You think you understand big. You don't. Every number you've ever held in your head, every distance you've ever imagined driving or flying or seeing, every mental model of vastness you've constructed from photographs and documentaries and childhood dreams about space, all of it, every single reference point, is a rounding error, a whisper, a speck of dust on the surface of something so large that calling it large stops meaning anything at all. The observable universe is 93 billion light-years wide. That is not a metaphor. That is not an estimate designed to sound impressive. That is the actual, measured span of everything we can theoretically see from Earth, the boundary drawn by the speed of light and the age of the cosmos itself. And here is the part that should keep you awake tonight. Most scientists believe that the true universe, the full structure beyond what light has had time to reach us, is at least 250 times larger than that. Some models suggest it may be infinite, not big, not huge, infinite. This video is going to take you on a journey through every scale of existence. We will start where your intuition still works, here on Earth, at the edge of the solar system, and then we will keep going, past the Milky Way's 400 billion stars, past the local group, past the Laniakea Supercluster and its 100,000 galaxies, all the way out to the cosmic web, the largest known structure in the universe, a network of filaments and voids that organizes all matter across scales your brain was never built to process. And then we will go further still, because the observable universe, vast as it is, may be less than 1% of what actually exists. This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You live on a sphere of rock and metal, wrapped in a thin film of water and air, spinning through space at roughly 1,670 kilometers per hour at the equator. You don't feel it. You never have. To you, the ground is still, the horizon is flat, the sky is up. And for most of human history, that was enough. We built cities, fought wars, crossed oceans, and never once needed to think about the fact that our entire world is a ball. Earth has an equatorial diameter of about 12,756 kilometers. That's 7,926 miles if you grew up with miles. The circumference, the distance around the fattest part of the planet, runs roughly 40,000 kilometers. If you started walking right now at a steady pace and never stopped, never slept, never ate, just walked in a straight line around the equator, it would take you about a year to return to where you started. That's assuming you could walk on water, which you can't, and that nothing killed you along the way, which it probably would. But the point stands. Earth is big. Big enough that for thousands of years, most people never traveled more than a few dozen kilometers from where they were born. Big enough that the idea of a round Earth seemed absurd to anyone who hadn't sailed far enough to watch the stars shift. And yet, compared to what's out there, Earth is a pebble, a dot, a rounding error in the accounting of cosmic mass. We are the largest rocky planet in our solar system. We are also the densest. Pack for pack, kilogram for kilogram, nothing in our neighborhood is squeezed tighter than we are. That should feel like an accomplishment. It doesn't, because the competition is embarrassing. Start with Mercury, the closest planet to the Sun. Mercury has a diameter of about 4,879 kilometers. That's roughly a third the size of Earth. You could fit 3 Mercuries side by side and still have room left over before you matched our width. From the surface of Mercury, the Sun looms enormous, more than twice as large in the sky as it appears from Earth. The planet itself is a scorched, airless ball of craters, baked on one side and frozen on the other, tidally locked into a slow waltz with the star it can never escape. Standing on Mercury, you would see the Sun as a bloated disk of fire taking up a terrifying portion of the sky. You would also be dead within seconds, but the view would be striking. Venus comes next, almost Earth's twin in size. Its diameter is 12,104 kilometers, just a few hundred kilometers shy of ours. But that's where the similarities end. Venus is a nightmare wrapped in clouds. The atmosphere is so thick and so hot that the surface pressure would crush you like a soda can, and the temperature sits around 465 degrees Celsius, hot enough to melt lead. Hot enough that early Soviet landers, built like tanks, lasted less than 2 hours before their electronics cooked. The clouds are sulfuric acid, the sky is a perpetual yellow haze, and the whole planet rotates backwards, slowly, taking longer to spin once on its axis than it does to complete an orbit around the Sun. Venus is what happens when a planet goes wrong. Mars is smaller, about 6,792 kilometers across, roughly half the width of Earth. It looks red because its surface is covered in iron oxide, rust, the kind you'd find on an old car left out in the rain. Mars has the largest volcano in the solar system, Olympus Mons, a shield volcano so massive it would cover the entire state of Arizona and stand 3 times taller than Mount Everest. It also has canyons that make the Grand Canyon look like a crack in the sidewalk, and it's cold. The average temperature sits around -60 degrees Celsius. The atmosphere is so thin that if you stood on the surface without a spacesuit, your blood would boil. Not from heat, from the lack of pressure. Mars is the closest thing we have to a second home in this system, and it would kill you just as efficiently as Venus, just in a different way. Then come the giants. Jupiter is 142,984 kilometers across. That's 11 times the diameter of Earth. You could line up 11 Earths in a row, edge to edge, and they would just barely span Jupiter's width. But diameter doesn't tell the whole story, volume does. You could fit about 1,410 Earths inside Jupiter and still have room to rattle them around. It's not a rocky planet, it's a gas giant, a ball of hydrogen and helium with no solid surface to stand on. If you tried to descend through Jupiter's atmosphere, you would fall for hours, then days, through layers of clouds and storms, past winds moving faster than the speed of sound, until the pressure became so extreme that the hydrogen around you stopped behaving like a gas and started behaving like a liquid metal. You would be crushed long before you reached whatever core might be hiding at the center, if there even is one. Jupiter is less a planet and more a failed star, a clump of gas that never quite gathered enough mass to ignite fusion in its core. It's still trying. The planet radiates more heat than it receives from the Sun, leftover warmth from its formation still leaking out into space. Saturn is almost as large, about 120,536 kilometers across, 9 times Earth's diameter. You could fit roughly 844 Earths inside it. Saturn is famous for its rings, which are made of billions of chunks of ice and rock, ranging in size from grains of sand to small houses. The rings are thin, less than a kilometer thick in most places, and they stretch out for hundreds of thousands of kilometers. From a distance, they look solid. Up close, they're mostly empty space, like everything else out here. Saturn itself is even less dense than Jupiter. If you could find a bathtub large enough, Saturn would float. Uranus comes next, about 51,000 118 kilometers across, 4 times the width of Earth. It holds roughly 64 Earths in volume. Uranus is tilted on its side, rotating at an angle so extreme that its poles take turns pointing directly at the Sun. Nobody knows why. The leading theory is that something massive, maybe another planet, maybe a moon, slammed into it early in the solar system's history and knocked it over. It never recovered. The planet is an icy blue ball of hydrogen, helium and methane, with winds that scream through its atmosphere at hundreds of kilometers per hour. Neptune is slightly smaller, about 49,528 kilometers across, but denser. It holds roughly 58 Earths. It's the farthest planet from the Sun, sitting about 19 times farther out than Earth. That distance matters because it changes everything. From Neptune, the Sun is no longer the overwhelming presence it is from Earth. It's just a bright star, slightly brighter than the others, but nothing you'd instinctively recognize as the center of your world. The light takes more than 4 hours to reach Neptune from the Sun. By the time you see the Sun move, it moved 4 hours ago. If the Sun exploded right now, Neptune wouldn't know for 4 hours. Neither would we, but we'd find out first. The distances between these planets are harder to grasp than their sizes because distance in space doesn't behave the way distance does on Earth. You can't walk it, you can't drive it. You can barely even conceptualize it without using tools that feel like cheating. Earth orbits the Sun at an average distance of about 93 million miles, roughly 149.7 million kilometers. That distance is called 1 astronomical unit, and it's the measuring stick we use for everything else in the solar system. Mercury sits at about 0.39 astronomical units from the Sun, Venus at 0.72, Mars at 1.52, Jupiter at 5.2, Neptune at 30. To put that in terms that don't require a calculator, if you were standing on Earth and you wanted to visit Mars, you'd have to travel at least 54 million kilometers, and that's only if you launched at the exact moment when Mars and Earth were on the same side of the Sun. Miss that window and the distance stretches to more than 400 million kilometers. A spacecraft like New Horizons, one of the fastest objects humanity has ever built, would take about 6 months to reach Mars. It took New Horizons about 10 years to reach Pluto, which sits roughly 367 billion miles from the Sun at its farthest point. And Pluto isn't even the edge of the solar system, not even close. The real edge, the true boundary, where the Sun's influence finally fades into the background noise of interstellar space, is a region called the Oort cloud. It's a spherical shell of icy debris left over from the formation of the solar system, scattered chunks of rock and frozen gas drifting in slow, lonely orbits around the Sun. The Oort cloud starts at about 2,000 astronomical units from the Sun and stretches outward to somewhere around 100,000 astronomical units. That's roughly 1.5 to 3 light years. A light year, for reference, is the distance light travels in 1 year, moving at 300,000 kilometers per second. It's about 9.46 trillion kilometers. The Sun's gravity reaches that far, barely. Objects in the Oort cloud are still bound to the Sun, still technically part of our solar system, but they're so far out that they might as well be in another universe. New Horizons, moving at roughly 58,000 kilometers per hour, would take about 30,000 years to reach the inner edge of the Oort cloud. By the time it got there, if it's still working, every human alive today will have been dust for 28,000 years. Most of the solar system is empty, profoundly, unsettlingly empty. The Moon, our closest neighbor, sits about 239,000 miles from Earth. That's roughly 30 Earth diameters away. If you lined up 30 Earths in a row, edge to edge, they would just barely reach the moon. That gap, that short little hop by cosmic standards, represents the farthest any human being has ever traveled. 12 people have walked on the moon. The last one left in 1972. Since then, we've stayed close to home, circling our own planet in low orbit like a dog on a leash. The Sun itself is almost incomprehensibly larger than anything orbiting it. Its diameter is about 392 million kilometers, roughly 109 times the width of Earth. You could fit about 1 million Earths inside the Sun, or about 1,000 Jupiters. The Sun contains 86% of all the mass in the solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust and gas scattered between them, adds up to barely a rounding error. The solar system is not a collection of objects orbiting a star. It's a star with some debris. From Earth, the Sun dominates the sky. It's the source of nearly all the light and heat that makes life possible. You can't look directly at it without damaging your eyes. It's the center of everything, the thing around which our entire existence revolves. But that dominance fades with distance. From Jupiter, the Sun still looks like the Sun, but smaller, dimmer, about 1/25 as bright as it appears from Earth. From Neptune, it's just a point of light, brighter than the other stars, yes, but not by much. If you were standing on the surface of some frozen moon out there, assuming you could stand, and assuming you weren't immediately killed by the cold or the radiation or the lack of air, you would look up at the sky and see a field of stars. One of them would be the Sun. You might not even notice which one at first. The thing that defines our entire world, the object that makes everything possible, would be just another dot. And that's the key realization. That's where this starts to matter. The Sun, the largest object most people will ever think about, the thing that lights our days and warms our skin and makes the plants grow, is unremarkable. It's a medium-sized star, slightly hotter and brighter than average, but nothing special. There are stars hundreds of times larger. There are stars thousands of times more luminous. There are stars so massive that if you replaced our Sun with one, its surface would extend past the orbit of Mars. And those stars are common. They're everywhere. You just can't see them with the naked eye because they're too far away. That's the scale problem in a nutshell. We start with something that feels infinite, Earth, and we realize it's tiny. We move to something that feels infinite, the solar system, and we realize it's a speck. We look at the Sun, the thing that makes the solar system matter, and we realize it's ordinary. And we're still in our own neighborhood. We haven't even left the driveway yet. We haven't crossed the street. We haven't left the block. The Oort cloud, the true edge of the Sun's domain, stretches outward for light years. Plural, more than one. It takes light, the fastest thing in the universe, multiple years to cross the full width of our solar system's influence. And that entire region, that vast sphere of emptiness with a few icy rocks scattered around the edges, is one solar system, one star's territory. There are more stars in the observable universe than there are grains of sand on every beach on Earth. Each one of those stars has its own version of this, its own planets, its own moons, its own debris field, its own edge where the light fades and the dark takes over. Our solar system is not small. It's enormous by any standard a human brain evolved to process, but it's also nothing. A single data point in a dataset so large that the numbers stop meaning anything. We built machines to measure it. We invented new units to describe it. We created models and simulations and maps, And every single one of them is a lie by omission, because the only way to make the scale comprehensible is to leave out most of the empty space, and there's so much empty space. From here, from this baseline, we can start to climb. We can leave the sun behind and look outward to the stars around us. We can start asking what lies beyond the Oort cloud, beyond the farthest reach of the sun's gravity, out in the space between stars, where the light takes years to travel and the distances make the solar system look like a dot on a map. That's where the real scale begins. That's where the numbers stop making sense. That's where the universe stops pretending to be something a human mind can hold. The Milky Way is an island. That's what astronomers used to call it. An island universe, adrift in an ocean of darkness. The phrase fell out of fashion once we realized the ocean was full of other islands, billions of them, scattered so far apart that light takes eons to hop from one to the next. But the old name still fits, because from here, from inside the Milky Way, you can't see the edges. You can't step back and take a picture of the whole thing. You're standing on the shore of the island, looking out at the trees and the hills, and someone is asking you to describe the shape of the coastline from memory. It can't be done, not directly. So we measure it in pieces, star by star, one careful triangulation at a time, building a map of something too large to see. The Milky Way is a barred spiral galaxy. That name tells you two things. First, it has spiral arms, long graceful curves of stars and gas that wind outward from the center like water swirling down a drain. Second, it has a bar, a thick, elongated structure running through the core, made of older stars packed together in a dense rectangular blob. The bar feeds gas inward toward the center, where it ignites new stars, and it channels matter outward along the spiral arms, where more stars form in the denser regions. The whole structure rotates, slowly, like a wheel lying flat in space, not a solid wheel. A wheel made of individual stars, each one following its own orbit around the center, all of them moving at slightly different speeds depending on how far out they sit. The result is a shape that looks static in photographs, but is actually in constant motion. Stars drifting past one another over millions of years, the spiral pattern shifting and reforming like a wave that never breaks. The Milky Way is big, roughly 100,000 light-years across, though some newer measurements push that number higher, maybe 120,000, maybe 180,000, depending on where you draw the line. A light year, remember, is the distance light travels in 1 year. About 9.5 trillion kilometers, 100,000 of those. Try to picture it, and your brain will do what it always does when the numbers get too large. It will give up. It will file the number away under the mental category of very big and move on. That's fine. That's normal. The human mind did not evolve to hold distances like this. We evolved to estimate how far away the next hill was, how long it would take to walk to the river, whether that rustling in the grass was close enough to be a threat. Our sense of scale tops out somewhere around a few dozen kilometers, maybe 100 if we're being generous. Past that, it's all abstract. Maps and models and tricks of language we use to pretend we understand. But here's the thing, the Milky Way is not abstract, it's real. It's out there right now, wrapped around you like a cocoon you can't see in daylight. Every star you've ever looked at, every constellation you learnt as a child, every bright dot scattered across the summer sky, all of it is part of this one structure, the Milky Way, our galaxy, the thing we live inside, and most of the time you can't even see it. From a dark site, far from city lights, On a clear moonless night, you can see a faint band of light stretching across the sky. The ancient Greeks called it Galaxies Cyclus, the Milky Circle. The Romans shortened it to Via Lactea, the Milky Way. Other cultures had their own names: the Road of Spirits, the Backbone of Night, the Silver River. All of them were describing the same thing: the combined glow of billions of stars, too faint and too distant to resolve individually, blurred together into a soft, hazy stripe cutting the heavens in half. That stripe is the edge-on view of the galactic disk, the flat plane where most of the Milky Way's stars live. You're looking outward from inside the disk, along its length, seeing the cumulative light of everything stacked up in that direction. Turn your head and look perpendicular to the band, up or down relative to the plane, and there are fewer stars. Not because the universe ends in that direction, but because the Milky Way is thin, about 1,000 light-years thick in the disk. Thin like a dinner plate is thin, wide in 2 dimensions, narrow in the 3rd, but most people today have never seen the Milky Way, not really. Light pollution from cities washes it out, turning the night sky into a dull orange glow. You can still see the brightest stars, the ones close enough and luminous enough to punch through the glare, but the faint background sweep of the galaxy itself disappears. Entire generations have grown up without knowing what their own sky looks like. They know the moon. They know a few bright planets. They can point out the Big Dipper if someone asks. And that's it. The rest is blank. Not because the stars aren't there, but because we've covered them up with our own light, traded the view of the cosmos for street lamps and billboards and the flat artificial glow of a city that never sleeps. There's a whole generation of people who think the night sky is supposed to be empty. Who would look at a photograph of the Milky Way from a dark site and assume it was fake, edited, exaggerated, because they've never seen anything like it? Because we turned off the sky from any single point on the globe. On a clear night far from civilization, you can see at most about 2,500 stars with the naked eye. Some sources push that number up to 3,000. Either way, it's a rounding error. The Milky Way contains somewhere between 100 and 400 billion stars. Most estimates cluster around 200 billion. Let's use that number. 200 billion. You can see 3,000. That's 15%. You are seeing nothing. A handful of the closest neighbors, the ones bright enough and near enough to register on the back of your retina, and behind them, invisible, uncountable, unreachable, an entire galaxy of light that your eyes will never resolve. And it's not just stars. For every star in the Milky Way, there is at least one planet, probably more. Conservative estimates put the number of planets in our galaxy at around 100 billion. More generous models push it past 400 billion. Some of those planets are gas giants like Jupiter, bloated balls of hydrogen with no surface to land on. Some are rocky, Earth-sized, orbiting in the habitable zone where liquid water could exist. Some are frozen ice worlds. Some are scorched cinders, circling too close to their parent stars. We've only just started cataloging them. NASA's Kepler mission, launched in 2009, spent 4 years staring at a single patch of sky containing about 150,000 stars. It found more than 2,600 confirmed planets in just that one tiny region. Extrapolate that across the whole galaxy, and the numbers get absurd. Hundreds of billions of worlds. Most of them will never be named. Most of them will never be visited. Most of them will drift through space for billions of years, circling their stars in silence, and no intelligent creature will ever look at them, or wonder what they are, or care that they existed at all. Our solar system sits about 27,000 light-years from the center of the Milky Way. We're not in the suburbs, we're not at the edge. We're somewhere in the middle, tucked into a minor spiral arm called the Orion Arm. It's not even a full arm. It's more like a spur, a short branch connecting two larger structures, the Sagittarius Arm inward and the Perseus Arm farther out. The Orion Arm is about 3,500 light-years across and roughly 10,000 light-years long. That's our neighborhood. That's the stretch of the galaxy we occupy, along with a few 100 million other stars. The brightest stars in the night sky, the ones humans have been naming for thousands of years, almost all of them are in the Orion Arm. Sirius, the brightest star in Earth's sky, sits about 6 light-years away, practically next door. Betelgeuse, the massive red supergiant in Orion's shoulder, is about 550 light-years out. Rigel, the blue giant at Orion's foot, sits roughly 860 light-years away. All of them are close by galactic standards, still impossibly far by any measure a human can relate to. If you left Earth today on the fastest spacecraft we've ever built, Voyager 1, traveling at roughly 61,000 kilometers per hour, it would take you about 70,000 years to reach the nearest star, and that's the nearest one. Proxima Centauri, just over 4 light-years away. A single hop across the block. 70,000 years. The Sun orbits the center of the Milky Way at a speed of about 828,000 kilometers per hour. That's more than 200 kilometers per second. You don't feel it. You're moving with it. Everything in the solar system is moving with it. The Earth, the Moon, Jupiter, the asteroids, the Oort cloud, all of it locked into the same slow, wide orbit around the galactic core. One complete orbit takes about 250 million years. Astronomers call that span a galactic year. The last time the Sun was in this position, this exact spot relative to the center of the Milky Way, the dinosaurs were just starting to diversify. Reptiles were beginning to dominate the land. The supercontinent Pangaea was still mostly intact. The Earth has made a little more than 18 full trips around the galaxy since it formed 5 billion years ago, 18 galactic years. Humans, modern Homo sapiens, have been around for maybe 300,000 years. That's about 12% of one galactic year, a blink, a fraction of a single tick. We appeared, built civilization, invented writing, walked on the moon and pointed telescopes at the sky, all within a rounding error of the Milky Way's rotation. The center of the galaxy is a strange place. You can't see it with visible light because the view is blocked by thick clouds of dust. But we can see it in infrared, in radio waves, in X-rays, and what we see is a supermassive black hole. Its name is Sagittarius A star, abbreviated SCR A star, and it weighs about 3 million times the mass of our Sun. The event horizon, the point of no return, where even light can't escape, has a diameter of roughly 6 million miles. That's about 5 million kilometers. If you dropped Sagittarius A star into our solar system and centered it where the Sun is, the event horizon would extend almost to the orbit of Mercury. Not quite touching, but close enough that Mercury would be doomed, spiraling inward over time as it lost energy to gravitational radiation. The black hole would swallow it eventually, quietly, without fuss. That's what black holes do. They wait. We've known about Sagittarius A star since 1974, when astronomers first detected it as a compact radio source at the galactic center. But we didn't know it was a black hole. Not for sure. Not until we watched stars orbiting it. In the 1990s, Two teams of astronomers, one led by Reinhard Genzel in Germany and the other by Andrea Ghez in the United States, began tracking the orbits of stars near the galactic center using some of the most powerful telescopes on Earth. They watched the same stars year after year, plotting their positions, measuring how fast they were moving. Some of those stars were screaming around the center at thousands of kilometers per second, whipping through their orbits in just a few years. The fastest one, a star called S2, completes a full orbit in 16 years. To move that fast, to stay bound in such a tight loop, something extraordinarily massive had to be sitting at the center, something invisible. The math pointed to a black hole. In 2008, Genzel and Ghez independently confirmed it. Sagittarius A star was real. It was a supermassive black hole, and it was sitting right in the middle of our galaxy, quietly pulling everything around it into a slow, inescapable spiral. In 2020, they won the Nobel Prize for the work. Most of the mass in the Milky Way is not stars, it's not gas, it's not dust, it's not even the supermassive black hole at the center. Most of the mass is dark matter, an invisible substance that doesn't emit light, doesn't absorb light, doesn't interact with normal matter except through gravity. We only know it's there because we can see its effects. Galaxies rotate too fast. The stars at the outer edges are moving so quickly that they should fly off into space, but they don't. Something is holding them in, something with mass, something we can't see. The best estimates suggest that about 85 to 90% of the Milky Way's mass is dark matter, spread out in a vast halo that extends far beyond the visible edges of the galaxy. The rest, the normal matter we can actually detect, stars and gas and dust, makes up only about 10%. Of that 10%, roughly 85% forms stars. The remaining 15% is scattered gas and dust drifting between the stars, raw material waiting to collapse into the next generation. The Milky Way's total mass, including all the dark matter, was once estimated at about 1.29 trillion times the mass of our Sun. That number came from a 2019 study that used a combination of stellar observations and computer models to weigh the galaxy. But in September 2023, a new study revised that estimate downward, way downward. The updated virial mass came in at just 206 billion solar masses, roughly 1/10 of the earlier figure. The revision came from better measurements of how stars move in the outer halo, where the dark matter's influence should be strongest. The new number is still enormous, still incomprehensible by human standards, but it's a reminder that even our best models are guesses, educated guesses, precise guesses, guesses backed by decades of data and some of the most sophisticated mathematics ever developed, but guesses nonetheless. We're standing inside the thing we're trying to measure, surrounded by stars and dust and invisible matter, trying to weigh it all from the inside. It's like trying to estimate the size of a forest while standing in the middle of it at night with a flashlight. You can count the trees nearby. You can make assumptions about the rest. You can't be sure. The Milky Way is not finished. It's still growing. Galaxies grow by eating each other, pulling in smaller neighbors with gravity and shredding them apart, scattering their stars into the larger structure. We've caught the Milky Way in the act. Right now, several smaller galaxies are in the process of being devoured. The Sagittarius dwarf elliptical galaxy, one of the closest, is being torn apart by tidal forces as it passes through the Milky Way's disk. Its stars are being pulled into long streams that wrap around our galaxy like ribbons. Eventually, those stars will be indistinguishable from the rest of the Milky Way's halo. The smaller galaxy will disappear, not destroyed, absorbed. The Milky Way is also on a collision course with the Andromeda Galaxy, the nearest large spiral, sitting about 5 million light-years away. In roughly 5 billion years, the two galaxies will collide. Not crash, collide. Galaxies don't smash into each other like billiard balls, they pass through each other. The stars are so far apart that almost none of them will actually hit. But the gravitational interaction will scramble both galaxies, flinging stars into new orbits, igniting bursts of star formation where gas clouds collide, and eventually merging the two structures into a single larger elliptical galaxy. Astronomers have already named it Milky Way. Our Sun, if it's still around, will probably survive the collision. It might get flung into a different part of the merged galaxy. It might get kicked out entirely, sent wandering through intergalactic space. Nobody knows. By that time, the Sun will be nearing the end of its life, swelling into a red giant, and the Earth, if it still exists, will be a charred cinder orbiting a dying star. So the collision won't matter much to us, but it will happen, and when it does, the Milky Way as we know it will cease to exist. It will become something else, something larger, something we'll never see. The Milky Way forms about 7 new stars every year. That might sound like a lot. It isn't. The galaxy is enormous. 7 stars per year across 200 billion existing stars is a rounding error. Meanwhile, stars are dying. Massive stars exhaust their fuel and go supernova, exploding in bursts of light that briefly outshine entire galaxies. Smaller stars like our Sun swell into red giants, shed their outer layers, and fade into white dwarfs. The birth rate roughly balances the death rate, so the total number of stars stays more or less constant for now. Eventually, billions of years from now, the galaxy will run out of gas. Star formation will slow, then stop. The Milky Way will grow darker as the remaining stars age and die, until all that's left is a graveyard of white dwarfs, neutron stars, and black holes drifting in silence. That's the far future, the heat death, the long, slow fade. It won't happen for trillions of years, long after the Sun is gone. Long after every structure humans have ever built has crumbled into dust. Long after the last recognizable remnant of Earth has vanished, the Milky Way will still be here, dimming slowly, winding down like a clock that nobody remembers to wind. The galaxy has structure. It's not a random scattering of stars, it's organized. The spiral arms, the bar, the central bulge, the halo. Each region has a different population of stars, a different density, a different history. The central bulge is crowded, packed with older stars, yellower, redder, stars that formed when the galaxy was young and have been drifting in slow, chaotic orbits ever since. The disk is thinner, flatter, home to younger stars and active star-forming regions, places where gas clouds are collapsing under their own gravity, lighting up new suns. The halo is sparse, a diffuse cloud of old stars and globular clusters scattered around the galaxy like a swarm of bees. The globular clusters are dense spherical collections of stars, hundreds of thousands of them packed into a region only a few dozen light-years across. They're some of the oldest structures in the galaxy, dating back more than 12 billion years, relics from a time when the Milky Way was still taking shape. And all of this, all 200 billion stars, all the planets, all the gas and dust and dark matter, all of it is just one galaxy, one island. One structure in a universe that contains at least 200 billion other galaxies, maybe more, scattered so far apart that the light from one takes millions or billions of years to reach the next. The Milky Way is home. It's the entire stage on which human history has played out. Every war, every discovery, every birth and death, every moment of joy or suffering, All of it happened here, inside this one galaxy, on one planet, orbiting one star, in one minor arm of a structure so large that we can't even see its edges from where we stand. And it's nothing. A single thread in a web that stretches across billions of light years. A single note in a symphony so vast that we can only hear a few bars of it, the parts close enough for our instruments to catch. The Milky Way is not alone. That might seem obvious after everything we've just covered, but it's worth saying explicitly because for most of human history, it wasn't obvious at all. For most of recorded time, people looked up at the night sky and saw the Milky Way, that faint band of light cutting across the darkness, and assumed it was the entire universe, everything, all of it. The stars, the planets, the moon, the sun, the hazy stripe overhead, that was the cosmos, complete, finished, wrapped up in a neat package that fit comfortably inside a single human lifetime of observation. Then, in the early 20th century, Edwin Hubble pointed a telescope at a fuzzy spiral-shaped patch of light called Andromeda and discovered it wasn't a nebula inside our galaxy. It was another galaxy entirely. A whole separate island universe, millions of light years away, containing hundreds of billions of stars of its own. The universe got bigger that day, much bigger, and it's been getting bigger ever since. The Milky Way belongs to a structure called the local group. The name is almost aggressively mundane, the kind of label you'd give to a neighborhood homeowners association, not a cosmic structure containing trillions of stars. But that's what astronomers called it in 1936, when Hubble first described it in his book, The Realm of the Nebulae. He called it a typical small group of nebulae, which is isolated in the general field. Typical, small, isolated. 3 words that perfectly capture how astronomers talk about things that would shatter a normal person's sense of scale. The local group is a gravitationally bound cluster of galaxies, meaning all the galaxies inside it are stuck together by their mutual gravity, orbiting around a common center of mass, slowly drifting toward one another, or circling each other in long, lazy loops that take billions of years to complete. The whole structure spans roughly 10 million light-years across. That's the diameter, edge to edge. 10 million light-years. We're still using light-years because kilometers stopped being useful a long time ago. A light-year, remember, is about 9.46 trillion kilometers, 10 million of those. If you tried to cross the local group at the speed of light, it would take you 10 million years. You would leave Earth today, travel faster than anything in the known universe, faster than causality itself allows for matter, and you wouldn't reach the far edge until 10 million years had passed. By then, the human species, if it still exists, will have evolved into something unrecognizable. Civilization as we know it will be a faint archaeological footnote, and you'll still be crossing a single neighborhood. When Hubble first catalogued the local group, he listed 12 members. He ranked them by brightness. Andromeda came first. The Milky Way came second. Then Triangulum, the large Magellanic Cloud, the small Magellanic Cloud, and a handful of smaller dwarf galaxies that barely registered on the photographic plates of the era. By 2003, the list had grown to 36 galaxies. Not because new galaxies had appeared, but because our instruments had improved enough to spot the faint ones, the dim, irregular blobs of stars drifting at the edges, too small and too dark to show up on early surveys. Today, the count sits somewhere between 50 and 134 galaxies, depending on which survey you trust and where you draw the boundary. Most of them are dwarfs. Tiny things, relatively speaking, containing only a few billion stars each. Some contain only a few million. A few of them are so faint and so diffuse that we're still not entirely sure they qualify as galaxies at all. They might just be loose streams of stars, debris left over from older collisions, slowly dissolving into the background. The exact number doesn't matter as much as the pattern. The local group is dominated by two massive spiral galaxies, the Milky Way and Andromeda, and everything else is just orbiting debris. Andromeda is the largest galaxy in the local group. Its official designation is Messier 31, M31 for short, named after the French astronomer Charles Messier, who catalogued it in 1764. But everyone calls it Andromeda, after the constellation where it appears in Earth's sky. It sits about 5 million light-years from the Milky Way. Some estimates put it closer, around 2 million light-years. Others stretch it to 7 million. The uncertainty comes from the difficulty of measuring distances at that scale. You can't just point a ruler at it. You have to use secondary methods, things like Cepheid variable stars, whose brightness fluctuates in a predictable way that correlates with their true luminosity. Measure the period of fluctuation, calculate the intrinsic brightness, compare it to how bright it looks from Earth, and you get a distance. It's clever, it works, but it's also built on a stack of assumptions, and every assumption carries error bars. So we say 5 million light-years, and we accept that it's close enough. Andromeda is a barred spiral galaxy, just like the Milky Way. It's wider, roughly 220,000 light-years across, more than twice the diameter of our galaxy, depending on whose measurements you trust. It contains somewhere around 1 trillion stars. 1 trillion. That's 5 times as many as the Milky Way, maybe more. The total mass, including dark matter, sits around 1 trillion solar masses, roughly the same as our galaxy's older mass estimate before the 2023 revision. Whether Andromeda is actually more massive than the Milky Way has been a subject of debate for years. Older studies said yes. Newer studies, using more precise measurements of stellar velocities, suggest the two galaxies might be roughly equal in mass, or that the Milky Way might even be slightly heavier once you account for all the dark matter we can't see. Either way, they're in the same weight class. Two heavyweight spirals circling each other in a slow gravitational dance that will eventually end in a collision. From Earth, on a clear night far from city lights, you can see Andromeda with the naked eye. Not clearly. It looks like a faint fuzzy smudge, a little oval patch of light sitting just off the main line of the Andromeda constellation. It's the most distant object visible to the unaided human eye. The light you're seeing left Andromeda 5 million years ago, back when early humans were still figuring out how to chip stones into tools. Homo habilis was walking around Africa. Homo sapiens didn't exist yet. The light traveled through space the entire time our species was evolving, crossing the void at 300,000 kilometers per second, and it arrived just in time for you to glance up at the sky one night and notice it. You're not seeing Andromeda as it is now. You're seeing it as it was, long before anything remotely human walked the Earth. And if someone in Andromeda, assuming there's anyone there to look, pointed a telescope at the Milky Way tonight, they wouldn't see us. They'd see the Milky Way as it was 5 million years ago. The sun would still be there, the Earth would still be there, but no cities, no lights, no radio signals, just a planet full of rocks and water, and the earliest ancestors of something that might one day wonder what else is out there. The two galaxies are moving toward each other, not quickly by everyday standards, but quickly by cosmic ones. Andromeda is approaching the Milky Way at roughly 110 kilometers per second. Some measurements push that up to 123 kilometers per second. Either way, it's fast. about 400,000 kilometers per hour. If you could stand in empty space halfway between the two galaxies and watch them approach, which you couldn't because you'd be dead, and also because galaxies don't appear to move on human timescales, they would be closing the gap at more than 100 kilometers every second. And they've been doing this for billions of years. The distance between them used to be much larger. It's shrinking. In roughly 3 to 4 billion years, depending on whose simulations you trust, the two galaxies will collide. Collide is the wrong word. It implies a crash, two solid objects smashing into each other and shattering. Galaxies don't work like that. Galaxies are mostly empty space. The stars inside them are so far apart that when two galaxies pass through each other, almost none of the stars actually hit. Think of it this way. If you scaled the Sun down to the size of a grain of sand, the nearest star, Proxima Centauri, would be another grain of sand sitting about 7 kilometers away. That's the density we're talking about. Two galaxies colliding is more like two clouds of gnats passing through each other. The gnats don't hit, they just intermingle. Their paths get scrambled by the gravitational pull of the overall swarm, and by the time the clouds separate, if they separate, every gnat is in a different place than it started. That's what will happen to the Milky Way and Andromeda. As the two galaxies approach, their outer halos will start to interact first. Dark matter halos, vast invisible structures that extend far beyond the visible edges of both galaxies, will pass through each other and start pulling on the stars inside. The spiral arms will distort. Stars will get flung into new orbits, some of them kicked out of their home galaxies entirely, sent wandering into the space between. Gas clouds in both galaxies will collide. Not the stars, but the diffuse clouds of hydrogen and helium drifting between them. And when gas clouds collide, they compress. Compressed gas heats up, collapses, and ignites into new stars. The collision will trigger a massive burst of star formation, lighting up both galaxies with millions of newborn suns. From a distance, the whole thing will glow brighter for a few 100 million years, a temporary flare of activity before things settle down. And then the two galaxies will pass through each other, their cores missing on the first pass, their stars and gas now intermixed. Gravity will pull them back together. They'll swing around, fall toward each other again, pass through a second time, then a third. Each pass will scatter more stars, strip away more gas, and pull the two structures closer. Eventually, after a few billion years of this slow, violent dance, they'll merge completely. The two spiral galaxies will become one large elliptical galaxy, a smooth blob of stars with no distinct arms, no organized rotation, just a chaotic swarm of suns drifting in random orbits around a common center. Astronomers have already named it Milkomeda. Some prefer Milkdromeda. Either way, it's the future. Our galaxy's future, assuming we're still around to see it, which we almost certainly won't be. By the time the merger completes, the Sun will be near the end of its life. It will have swollen into a red giant, its outer layers expanding past the orbit of Venus, possibly past Earth's orbit, depending on how much mass it loses along the way. The Earth itself, if it hasn't been swallowed, will be a charred, lifeless rock, baked sterile by a sun that's 100 times larger than it is today. Life on Earth, if any remains, will have moved elsewhere or gone extinct. The Milky Way as we know it will no longer exist. Andromeda as we know it will no longer exist. They'll both be gone, absorbed into something new, something larger, something we'll never recognize as home. The third largest galaxy in the local group is Triangulum, also called M33. It's a small spiral, roughly 60,000 light-years across, sitting about 2.7 to 3 million light-years from the Milky Way. It contains somewhere around 40 to 50 billion stars, depending on the estimate. That's tiny compared to the Milky Way's 200 billion or Andromeda's trillion, but it's still a galaxy. Still billions of stars bound together by gravity, still rotating, still forming new stars in its spiral arms. Triangulum is thought to be a satellite of Andromeda, loosely bound to it by gravity, orbiting it the way the Moon orbits Earth, but on a much larger scale and over much longer timescales. When Andromeda and the Milky Way collide, Triangulum will probably get pulled into the merger. Its stars will scatter, its structure will dissolve, and it will become part of Milky Way. Or it might get ejected entirely, flung out into intergalactic space by the gravitational chaos of two much larger galaxies tearing into each other. Simulations show both outcomes as possible. Nobody knows which one will happen. It depends on the exact angles, the exact velocities, the exact distribution of mass in all three galaxies at the moment of collision. Small differences in initial conditions lead to wildly different results, and we don't know the initial conditions well enough to say for sure. Closer to home, the Milky Way has its own satellites. The two most famous are the Large Magellanic Cloud and the Small Magellanic Cloud, irregular dwarf galaxies orbiting the Milky Way like moons. The Large Magellanic Cloud sits about 163,000 light-years from Earth. The Small Magellanic Cloud is farther out, roughly 202,000 light-years away. Both are visible from the southern hemisphere with the naked eye. They look like detached pieces of the Milky Way, faint smudges of light hovering near the main band. Early European explorers didn't know what they were. The indigenous people of the southern hemisphere had their own names and stories for them, but those stories were ignored or erased by the colonial powers that mapped the skies and decided what counted as knowledge. The clouds were eventually named after Ferdinand Magellan, the Portuguese explorer who led the first expedition to circumnavigate the globe in the early 1500s, even though he didn't discover them and had nothing to do with figuring out what they were. That's how history works sometimes. The wrong names stick. The Large Magellanic Cloud contains roughly 30 billion stars. The Small Magellanic Cloud has about 3 billion. Both are irregular galaxies, meaning they don't have a defined spiral or elliptical shape. They're just loose blobs of stars, distorted and stretched by the Milky Way's gravity as they orbit. Eventually, probably in a few billion years, the Milky Way will tear them apart completely and absorb their stars into the halo. It's already started. Streams of stars pulled from the Magellanic Clouds have been detected wrapping around the Milky Way, thin trails of debris marking the path of their slow disintegration. The galaxies are dying. Not quickly, not violently, but inevitably. Tidal forces are pulling them apart, star by star, and there's nothing that can stop it. In a few billion years, the Magellanic Clouds will no longer exist as separate structures. They'll be part of the Milky Way, their stars scattered and mixed, their original shapes erased. The rest of the local group is made up of dozens of smaller dwarf galaxies. Most of them are satellites of either the Milky Way or Andromeda. A few are drifting freely in the space between, loosely bound to the whole group, but not tied to any single large galaxy. Most of these dwarfs are dim, containing only a few million to a few billion stars. Some are so faint and so spread out that they were only discovered in the last few decades, hidden in the glare of the Milky Way, or buried in the noise of background stars. One of the smallest known members of the local group is a galaxy called Segway 2. It contains only about 1,000 stars. 1,000. That's less than the number of people in a small town. You could count them individually if you had enough time and patience. Whether Segway 2 even qualifies as a galaxy or whether it's just a large star cluster is still debated. The line between the two is blurry. At some point, a collection of stars stops being a cluster and starts being a galaxy, but nobody has agreed on exactly where that line sits. Most of the space in the local group is empty. That needs to be said clearly because the numbers make it easy to forget. The local group spans 10 million light-years. It contains somewhere between 50 and 134 galaxies, depending on how you count. The two largest galaxies, the Milky Way and Andromeda, account for most of the visible mass. If you add up all the stars in all the galaxies in the local group, you get somewhere around 3 to 1, 5 trillion stars. That's an enormous number. It's also almost nothing when you spread it across 10 million light-years. Most of the volume is void, empty space, a near-perfect vacuum with the occasional hydrogen atom drifting through, maybe a photon from a distant star, maybe a stray cosmic ray. You could fly through the local group in a straight line for millions of years at the speed of light and never come close to a star. The distances between galaxies are vast beyond comprehension. Even the distances between stars within a single galaxy are vast. But the distances between galaxies are worse. They're so large that even light, the fastest thing in the universe, takes millions of years to cross them. If you pointed a spaceship at Andromeda today and traveled at 17.3 kilometers per second, a speed faster than anything humans have ever built, it would take you 40 billion years to get there. The universe is only 13.8 billion years old. You would be traveling for 3 times the current age of the universe, and you still wouldn't have left the local group. Gravity holds the local group together. Every galaxy inside it is pulling on every other galaxy, a slow tug-of-war that plays out over billions of years. The Milky Way and Andromeda dominate because they're the most massive. Their gravity controls the motion of everything else in the group. The smaller galaxies orbit them, spiral in toward them, or get torn apart by them. There's no escape. Once you're inside the gravitational well of a structure this large, you're stuck. The local group is a closed system, sealed off from the rest of the universe by the sheer distance to the next nearest galaxy group. And over time, over tens of billions of years, the entire local group will merge into a single massive elliptical galaxy. All the spirals will unwind, all the dwarfs will be absorbed. All the stars will be redistributed into one giant blob, slowly rotating, slowly cooling, slowly fading as the last generation of stars burns out and dies. That's the long-term future. Not collapse, not destruction, just merger. Everything in the local group will become part of one structure, and that structure will sit alone in an expanding universe, drifting farther and farther from the other galaxy groups as space itself stretches between them. The local group is also moving. Not just the internal motion of galaxies orbiting each other, but the whole structure is drifting through space as a unit. It's being pulled toward a massive concentration of galaxies called the Virgo cluster, a much larger structure sitting about 65 million light-years away. The Virgo cluster contains more than 1,000 galaxies, some of them far larger and more massive than anything in the local group. The combined gravity of all those galaxies is pulling us toward it, slowly, inexorably. At the same time, the local group is being pushed from behind by something called the dipole repeller, a vast, empty region of space where the lack of matter creates a kind of negative pressure, shoving everything away from it. Between the pull from Virgo and the push from the repeller, the local group is moving through space at hundreds of kilometers per second, carried along by forces so large that no individual galaxy can resist them. And beyond Virgo, there are even larger structures. The Virgo cluster itself is part of the Virgo Supercluster, a vast web of galaxies spanning more than 100 million light-years. And the Virgo Supercluster is part of something even larger, a structure so immense that it wasn't fully mapped until 2014, more than 70 years after Hubble first described the local group. That structure has a name, Laniakea. It means immeasurable heaven in Hawaiian, and it is the cosmic home of everything we've talked about so far. The local group, the Virgo cluster, the superclusters, all of it is just a small part of Laniakea, and Laniakea is just one structure among thousands scattered across the observable universe. The scale doesn't stop, it keeps growing. Every time you think you've found the edge, you realize you're still in the middle. The local group is not the top of the hierarchy. That might seem obvious after spending this much time climbing the ladder of cosmic scale, but it's worth stating plainly because the human brain has a nasty habit of deciding it's reached the edge of something, when really it's just hit the edge of what it can comfortably imagine. The local group, that collection of 50 to 100 and something galaxies spread across 10 million light-years, is not a standalone structure. It's not floating in isolation. It's part of something larger, much larger. A structure so vast that astronomers didn't even realize it existed as a coherent thing until 2014, more than 80 years after Edwin Hubble first catalogued the galaxies in our neighborhood. The structure has a name, Laniakea, and it is the cosmic address of everything we've talked about so far. Laniakea is a supercluster. That word, supercluster, is exactly what it sounds like, a cluster of clusters. Take galaxy clusters, those enormous gravitationally bound collections of hundreds or thousands of galaxies, and group those clusters together into an even larger structure, and you get a supercluster. It's the next rung up on the ladder, the next level of organization in a universe that seems pathologically committed to building things in nested hierarchies. Atoms form molecules, molecules form cells, cells form organisms, organisms form ecosystems, stars form galaxies, galaxies form groups, groups form clusters, clusters form superclusters. The pattern repeats at every scale, from the microscopic to the cosmological, and nobody knows why. It's just what the universe does. It clumps. The term supercluster has been around since the 1950s, but the definition has always been slippery. Early maps of the universe identified regions where galaxies seemed unusually concentrated, vast sprawling webs of light separated by darker voids where almost nothing sat. Astronomers called those concentrations superclusters and drew rough boundaries around them based on where the density of galaxies dropped off. It was a start, but it was also imprecise. Density alone doesn't tell you much. Two galaxies can be close together in space, but not actually connected, just sitting near each other by coincidence, each drifting in a different direction with no shared future. To know if a supercluster is real, to know if it's a meaningful structure and not just a random overdensity, you need to look at motion. You need to track where the galaxies are going, not just where they are. That's what R. Brent Tully and his team at the University of Hawaii did. Starting in the early 2000s, they began mapping the motions of galaxies across a huge volume of space, measuring not just how fast galaxies were receding due to the expansion of the universe, which is straightforward, but also their peculiar velocities. Peculiar velocity is the term astronomers use for motion that's not caused by the expansion of space itself. It's the motion galaxies have because they're being pulled by gravity towards some massive concentration of matter nearby, or because they're falling into a cluster, or because they got kicked by a past interaction with another galaxy. It's the local motion, the motion that tells you what's actually happening in a given region of the universe beyond the overall expansion. Measure enough peculiar velocities, map them carefully, and you can trace the gravitational flow of matter across hundreds of millions of light years. You can see where galaxies are being pulled, and you can identify the boundaries where one flow ends and another begins. Tully's team used data from something called the Cosmic Flows 2 project, a massive survey that measured the distances and velocities of more than 8,000 galaxies scattered across the nearby universe. They took that data and applied a technique called watershed basin mapping. The name comes from hydrology, the study of water flow. If you look at a landscape from above, you can identify drainage basins, regions where all the water flows toward a common outlet, a river, a lake, a low point in the terrain. The boundaries between basins are called watersheds. Stand on a watershed, and the rain that falls on one side of you flows into one river system, while the rain on the other side flows into a completely different one. The same principle works for galaxies. Instead of water flowing downhill, you have galaxies flowing through space toward concentrations of mass. Map the flow carefully, and you can identify the watershed boundaries, the places where the flow changes direction, where one supercluster ends and the next begins. In September 2014, Tully's team published their results in the journal Nature. They had identified the boundaries of the supercluster containing the Milky Way. It wasn't the structure astronomers had been calling the local supercluster for decades. That older definition was too small, based on outdated methods that only looked at density. The real structure, defined by gravitational flow, was much larger. It stretched across roughly 520 million light-years. Some sources say 500 million, others say 400 million. The uncertainty comes from the same issue that's plagued every distance measurement we've talked about so far. The farther out you look, the harder it is to pin things down precisely, but the order of magnitude is clear. Hundreds of millions of light-years, a distance so large that light, traveling at 300,000 kilometers per second, takes more than 500 million years to cross from one edge to the other. The structure contains roughly 100,000 galaxies. That number is an estimate, not an exact count. You can't point a telescope at a region that large and catalogue every single galaxy. Many of them are too faint, too distant, or hidden behind dust and gas. But based on the density of galaxies in the regions we can see clearly and extrapolating outward, the total comes out to around 100,000. Each of those galaxies contains anywhere from a few million to a few trillion stars. Do the math, and you're looking at something on the order of 10 to the power of 15 stars, a quadrillion. Maybe more, spread across a volume so vast that the distances between galaxies, already incomprehensible at the scale of the local group, become just noise in the overall structure. The space between the Milky Way and Andromeda, that 2.5 million light-year gap that seemed enormous a few pages ago, is now a rounding error, a single pixel in a map that spans 500 million light-years. The total mass of Laniakea, including all the galaxies, all the gas, and all the dark matter holding it together, sits around 100 quadrillion times the mass of the Sun. That's 10 to the 17th solar masses. Another way to say it is that Laniakea weighs about 100,000 times as much as the Milky Way. Take our entire galaxy, every star, every planet, every black hole, every atom of gas drifting between the stars, and multiply it by 100,000. That's Laniakea. And Laniakea is just one supercluster among thousands scattered across the observable universe. It's not special. It's not unique. It's just the one we happen to live in, the way you happen to live in a particular city, in a particular country, on a particular continent. your address expanded to a cosmic scale. Tully and his team needed a name for the structure, and they chose Laniakea. It's a Hawaiian word. It means immense heaven or open skies, depending on how you translate it. The choice wasn't random. Tully works at the University of Hawaii, and many of the astronomers on his team have ties to the islands. Hawaiian navigators have a long history of using the stars to cross vast distances, navigating by the sky in ways that required an intimate understanding of celestial patterns. Naming the supercluster in Hawaiian was a nod to that tradition, a way of connecting the ancient practice of wayfinding to the modern practice of mapping the universe. It's also a beautiful name, Immense Heaven. It fits, because that's what Laniakea is. A heaven so immense that the word heaven, with all its connotations of vastness and infinity, barely scratches the surface. At the center of Laniakea, or near the center, depending on how you define it, sits something called the Great Attractor. That name is not a metaphor, it's a literal description. The Great Attractor is a massive gravitational anomaly, a region of space where the density of matter is so high that it's pulling everything nearby toward it, including us, including the Milky Way. The local group as a whole is moving toward the Great Attractor at roughly 600 kilometers per second. That's more than 2 million kilometers per hour, fast enough to cross the distance from Earth to the Moon in about 3.5 minutes. We've been falling toward it for billions of years, and we'll keep falling toward it for billions more. Not because we chose to, not because anything pushed us, just because that's what gravity does. It pulls. The Great Attractor was discovered in the 1970s, though the term wasn't coined until the 1980s. Astronomers noticed that galaxies in our region of the universe, including the Milky Way, were all moving in the same general direction, toward a point in the sky located in the constellation Norma. The motion couldn't be explained by the expansion of the universe alone. Something was pulling, something massive. The problem was that when astronomers pointed their telescopes at that region, they couldn't see much. The Great Attractor sits on the far side of the Milky Way's galactic plane, the flat disk where most of our galaxy's stars and gas are concentrated. All that intervening matter blocks visible light. It's like trying to see across a fog bank. You know something is on the other side because you can feel its effects, but you can't see it directly. Eventually, using infrared and X-ray telescopes that can see through dust, astronomers identified the Norma cluster, a massive cluster of galaxies sitting roughly 220 million light-years away in the direction of the Great Attractor. The Norma cluster is huge, containing dozens of large galaxies and contributing a significant chunk of the gravitational pull. But it's not the whole story. The Great Attractor isn't a single object. It's a region, a concentration of mass spread across tens of millions of light-years, made up of multiple galaxy clusters, all pulling together in the same general direction. The Norma cluster is the most prominent feature, but it's part of a larger gravitational well, and that well is what defines the center of Laniakea's flow. Galaxies across Laniakea are moving toward the Great Attractor, but they're not moving in straight lines. Gravity doesn't work like that. Every galaxy is being pulled by every other galaxy, and the result is a complex flow, a kind of cosmic river system where smaller streams merge into larger ones, all of them eventually feeding into the same basin. The local group is part of a flow that includes the Virgo cluster, a much larger structure sitting about 65 million light-years away. The Virgo cluster contains more than 1,000 galaxies, some of them far more massive than the Milky Way or Andromeda. It's one of the dominant structures in our region of Laniakea, and its gravity is pulling the local group toward it. At the same time, the Virgo cluster itself is being pulled toward the Great Attractor. and the Great Attractor is being pulled toward an even larger structure beyond Laniakea's edge, something called the Shapley Supercluster, which sits roughly 650 million light-years away and contains tens of thousands of galaxies. The flow doesn't stop. It keeps cascading, structure feeding into structure, all the way up to the largest scales the universe allows. Here's the uncomfortable part. Laniakea is not gravitationally bound. That sentence needs to sit for a second because it changes everything. A gravitationally bound structure is one where the mutual gravity of all the objects inside it is strong enough to hold them together against the expansion of the universe. The local group is gravitationally bound. The galaxies inside it will stay together, merge, and eventually form a single massive elliptical galaxy. The Virgo cluster is gravitationally bound. The galaxies inside it are stuck. They'll orbit each other, collide, merge, and remain part of the same structure for trillions of years. But Laniakea is not bound. The expansion of space is stronger than the gravity holding it together. And that expansion is accelerating. Roughly 6 billion years ago, the universe's expansion, which had been slowing down due to the gravitational pull of all the matter inside it, started speeding up. The cause is something called dark energy, a poorly understood force that seems to be pushing space itself apart. Dark energy is now the dominant force in the universe. It makes up about 68% of the total energy density of the cosmos. Dark matter makes up about 27%. Normal matter, the stuff we can see and touch and build things out of, accounts for less than 5%. Dark energy is winning. And because it's winning, structures like Laniakea, which are held together only by the relatively weak gravitational attraction of galaxies separated by hundreds of millions of light-years, are being pulled apart. Slowly, gently, but inevitably. Laniakea is dissolving, not collapsing, not exploding, just gradually coming undone as the space between its member galaxies stretches faster than their gravity can pull them back together. The flow of galaxies toward the Great Attractor is real. It's happening right now. But it's a temporary pattern, a snapshot of a structure that will not survive into the far future. In a few tens of billions of years, the galaxies at the edges of Laniakea will have been carried so far away by the expansion of space that they'll no longer be visible from the Milky Way. The light from them will be redshifted into invisibility. The supercluster as we know it will have ceased to exist, not because anything destroyed it, but because the universe grew too large for it to hold together. That makes Laniakea an apparent formation. It looks like a coherent structure when you map the flow of galaxies at this moment in cosmic history. But zoom out in time, look at the universe as it was 10 billion years ago, or as it will be 10 billion years from now, and the boundaries shift. The structure changes. What we call Laniakea is really just a particular configuration of matter at a particular moment, defined by the balance between gravity pulling inward and dark energy pushing outward. That balance is shifting in favor of dark energy, and eventually the supercluster will fade. For now, though, it's real, and it's our home. The Milky Way sits near the edge of Laniakea, not at the center. We're in the outskirts, drifting in one of the smaller flow basins, being pulled gently toward the Great Attractor, but too far out to be dominated by it. If you could somehow step outside Laniakea and look at it from a distance, assuming you could see it, which you couldn't because galaxies at that scale blur together into a faint haze, it would look like a network of filaments and nodes. Bright, dense clusters connected by long, thin threads of galaxies with vast, empty voids in between. The Great Attractor would sit near the center of mass, a bright knot where multiple filaments converge. The Virgo cluster would be another bright spot, closer to our position, a major hub in the network. And scattered around the edges, in the quieter regions where the density drops off, you'd find places like the local group. Small, dim, unremarkable. Laniakea is one of the smaller superclusters. That might seem hard to believe after spending this long talking about its size, but it's true. The shapely supercluster, which sits beyond Laniakea's edge and pulls on it gravitationally, is much larger. It contains tens of thousands of galaxies and weighs several times as much. Other superclusters scattered across the observable universe are larger still. The Hercules supercluster, the Coma supercluster, the Sloan Great Wall, a structure so large it defies the usual definition of a supercluster and is sometimes called a galactic filament instead. All of them are larger than Laniakea. All of them are held together, or held together loosely, by the same balance of gravity and expansion, and all of them are dissolving at different rates depending on their size and density. The discovery of Laniakea changed how astronomers think about cosmic structure. Before 2014, the standard picture was that the universe was organized into a hierarchy of discrete objects. Stars formed galaxies. Galaxies formed groups. Groups formed clusters. Clusters formed superclusters. Each level was a distinct thing, a clear-cut structure with a beginning and an end. Laniakea complicated that picture. By defining superclusters based on flow rather than density, Tully's team showed that the boundaries between structures are fuzzy. Laniakea doesn't have a sharp edge. It fades gradually into the regions around it, the flow weakening as you move outward until eventually you cross a watershed and find yourself in a different basin, being pulled toward a different attractor. The universe is not made of discrete objects stacked neatly on top of each other. It's made of overlapping flows, intersecting streams of matter moving through space under the influence of gravity and expansion, and the structures we identify are just the patterns those flows make at a given moment. That realization leads directly to the next level of scale, the one that finally starts to feel like the top of the hierarchy. Not because there's nothing larger, but because the structures at this scale are so vast that they begin to approach the size of the observable universe itself. Laniakea is part of something even bigger, a network, a web, a cosmic infrastructure made of filaments and voids that stretches across billions of light-years and contains every galaxy, every cluster, every supercluster we've talked about so far. That web has a name. Astronomers call it the cosmic web, and it is the largest structure in the universe, not the largest object. Objects have boundaries. The cosmic web is more like a skeleton, the underlying framework that defines where matter is and where it isn't, the scaffolding on which everything else is built. And once you see it, once you step back far enough to take in the full picture, the scale stops being about distance and starts being about something else entirely. It becomes about the limits of what we can observe, the edge of the visible universe, the boundary where the light hasn't had time to reach us yet and probably never will. That boundary sits 93 billion light-years away, and we're about to explain why a universe that's only 13.8 billion years old can have an edge that's 93 billion light-years out. But first, we need to look at the Webb. Laniakea is not drifting alone in the dark. That might be the impression you've gotten from everything so far, that superclusters are isolated structures floating through empty space like islands scattered across an infinite ocean. It's a tempting image. It's also wrong. Because when you step back far enough, when you zoom out past the local group and past Laniakea and past all the other superclusters scattered across the nearby universe, a pattern emerges. Not chaos, not randomness, a pattern. Matter in the universe is not distributed evenly, it's organized, threaded together into a vast interconnected network of filaments and voids that stretches across the entire observable cosmos. Astronomers call it the cosmic web, and it is the largest coherent structure in existence, not the largest object. Objects have edges. The cosmic web is more like a skeleton, the framework on which everything else hangs. And once you see it, once you understand what you're looking at, the universe stops being a collection of isolated points and starts being something else entirely, a machine, a pattern, a shape. The cosmic web is made of three components: filaments, voids, and nodes. Filaments are the threads, long, thin strands of galaxies and dark matter, stretching across hundreds of millions of light-years, connecting the denser regions of the universe like highways between cities. Voids are the gaps, vast regions of near-empty space, huge bubbles where almost nothing sits. No galaxies, no stars, just the occasional hydrogen atom drifting in the dark. Nodes are the intersections, the places where multiple filaments meet, where the density of matter spikes dramatically, where gravity pulls everything nearby into a single massive cluster. Galaxy clusters sit at the nodes. Superclusters like Laniakea stretch along the filaments, and the voids, the enormous empty spaces between the threads, account for most of the volume of the universe. Most of the cosmos is nothing, not metaphorically, literally. By far, most of the cosmic volume turns out to be empty. Here are the numbers, because without the numbers the scale doesn't hit. Filaments, the threads of the web, can stretch for several 100 million light-years. Some of the most prominent ones reach lengths longer than Laniakea's entire diameter. They're not thin like a rope. They're more like elongated clouds, diffuse structures several tens of millions of light-years wide, but much longer in one direction than the other. Galaxies inside the filaments are strung out along the length like beads on a string, not packed tightly but distributed loosely, following the flow of dark matter that defines the filament's shape. The filaments themselves are mostly dark matter. The galaxies are just markers, the visible parts of a structure that's mostly invisible. For every galaxy you can see in a filament, there's 100 times more mass in the form of dark matter threading through it, holding the whole structure together with gravity. Voids are bigger, much bigger. Typical voids have diameters ranging from 30 million to 300 million light-years. Some are even larger. The Boots void, one of the most famous, spans roughly 330 million light-years across and contains only about 60 galaxies. For context, a volume of space that size, if it were filled with the average density of the universe, should contain roughly 10,000 galaxies. The Boots void has 60. That's not empty by the strictest definition. There are galaxies in there. But compared to what should be there, compared to the rest of the universe, it's a desert, a void. The galaxies that do exist inside voids tend to be small, dim, and isolated, drifting through the emptiness with no neighbors for millions of light-years in any direction. If you lived in a galaxy inside a void, your night sky would be almost blank, no Milky Way band stretching overhead. No Andromeda, visible as a faint smudge, just a few scattered points of light, the stars of your own galaxy, and beyond that, darkness. The nearest other galaxy would be so far away that even with the best telescopes, you'd struggle to find it. Voids occupy the largest volume fraction of the universe. Roughly 70% of the universe's total volume is void, empty space. The filaments, the threads connecting everything, account for most of the rest. And the nodes, the galaxy clusters sitting at the intersections, take up less than 1% of the total volume, but contain about 10% of the universe's mass. That's the distribution. Most of the space is empty, most of the matter is in the filaments, most of the density is at the nodes. The universe is a sponge, a foam, a structure with a lot of surface area and very little interior, where the interesting parts are all concentrated in the thin walls between the bubbles. This wasn't obvious. For most of the 20th century, astronomers assumed galaxies were scattered more or less randomly across space. Sure, there were clusters, obvious concentrations where galaxies bunched together, but those were thought to be isolated structures, local overdensities in an otherwise uniform distribution. The idea that there might be large-scale organization, that galaxies might be arranged into a coherent pattern stretching across the entire universe, didn't gain serious traction until the 1980s. That's when systematic mapping of the cosmic web began. Astronomers started surveying large volumes of space, measuring the positions and distances of thousands of galaxies and plotting them on three-dimensional maps. And when they did, the pattern jumped out immediately. Galaxies were not randomly scattered, they were clustered along thin filaments, wrapped around the edges of enormous voids. The distribution looked less like a random spray of points and more like a spider web, a network of threads with gaps in between. The first major detection of this structure came from surveys of the local universe, the region within a few 100 million light-years of the Milky Way. Astronomers identified large voids, regions where the density of galaxies dropped off sharply, and they identified filaments, long chains of galaxies stretching from one cluster to the next. But the real breakthrough came with the Sloan Digital Sky Survey, a massive observational project that began in the year 2000 and spent more than a decade mapping the positions of millions of galaxies across a huge volume of space. The SDSS used a dedicated telescope in New Mexico to photograph the sky in multiple wavelengths, measure the redshifts of galaxies to determine their distances, and build a three-dimensional map of the universe. The resulting map was stunning. It showed the cosmic web in exquisite detail, filaments branching and intersecting, voids stacked next to voids, clusters sitting at the nodes where multiple filaments converged. The universe had structure, large-scale structure, and that structure was consistent across the entire surveyed volume. Wherever astronomers looked, they found the same pattern: filaments and voids, walls and bubbles, the cosmic web. Computer simulations confirmed it. Starting in the 1980s, physicists began running numerical models of the universe's evolution, starting from the conditions of the early cosmos and letting gravity do its work. They seeded the simulations with tiny density fluctuations, small variations in the distribution of matter left over from the Big Bang, and then let time run forward. The simulations tracked billions of particles, each one representing a clump of dark matter, as they moved through space under the influence of gravity. Over billions of simulated years, the particles clumped together. Small overdensities grew into larger ones. Dark matter collapsed into halos. Gas followed the dark matter, falling into the deepest gravitational wells. And as the simulation progressed, the distribution of matter organized itself into filaments and voids, exactly like the pattern astronomers were seeing in the real universe. The cosmic web wasn't imposed from the outside. It wasn't designed. It was a natural result of gravity acting on an uneven distribution of matter over billions of years. The pattern was inevitable. Run the simulation 1,000 times with slightly different starting conditions, and you'd get 1,000 different webs, but they'd all have the same basic structure: filaments, voids, nodes. The universe, it turns out, only knows how to build things one way. Dark matter is the key. Without dark matter, the cosmic web wouldn't exist. Normal matter, the stuff we can see, only accounts for about 5% of the total mass energy of the universe. The rest is dark matter and dark energy. Dark matter doesn't interact with light. It doesn't emit radiation, doesn't absorb radiation, doesn't reflect it. The only way we know it's there is through its gravitational effects. It pulls on normal matter. It bends the paths of light passing near it. And it clumps. Dark matter clumps more easily than normal matter because it doesn't have pressure pushing back. Normal matter, gas and plasma, heats up when you compress it. That heat generates pressure, and pressure resists further compression. Dark matter doesn't heat up. It just collapses, pulled together by gravity, with nothing to slow it down. In the early universe, dark matter collapsed first, forming the scaffolding of the cosmic web. The filaments and nodes of the web are dark matter structures. Normal matter followed later, falling into the gravitational wells that dark matter had already carved out, forming galaxies where the dark matter was densest. The galaxies we see today are sitting inside halos of dark matter, invisible cocoons that hold them in place and define their motion. The cosmic web is a dark matter web. The galaxies are just the lights strung along the frame. Luminous matter closely follows the dark matter distribution on cosmic web scales. That sentence is important because it tells you why the web is visible at all. If normal matter didn't follow dark matter, if it were scattered randomly across space, regardless of where the dark matter concentrated, we wouldn't see a web. We'd see noise. But normal matter does follow dark matter. Galaxies form where dark matter is dense. They cluster along filaments because the filaments are where the dark matter is concentrated. They sit at nodes because nodes are the deepest gravitational wells, the places where multiple filaments intersect and the combined mass of dark matter is highest. The pattern we see in the distribution of galaxies is a direct map of the underlying dark matter structure. The web is real. It's not an optical illusion. It's not a projection effect. It's the actual large-scale organization of matter in the universe, and it's held together by the gravity of something we can't see. The filaments are where most of the action happens. Filamentary networks contain half of the total cosmic matter in a relatively small volume. That's a staggering statistic. Half the mass of the universe, not counting dark energy, is concentrated in the thin threads of the cosmic web. The filaments are highways. Galaxies drift along them, pulled by gravity toward the nodes. Gas flows along them, funneled from the voids into the denser regions where it can collapse and form new stars. The filaments are feeding tubes, channels through which matter is constantly being redistributed, pulled from the empty regions and concentrated in the places where gravity is strongest. If you could speed up time and watch the universe evolve over billions of years, you'd see galaxies sliding along the filaments like beads on a wire, slowly spiraling inward toward the nodes. You'd see the voids growing larger as matter drained out of them, evacuated by the pull of the surrounding filaments. And you'd see the nodes getting denser, swelling as they accreted more and more mass from the filaments feeding into them. The cosmic web is not static. It's a flow system, a network of rivers carrying matter from one place to another, and the direction of flow is always the same, toward density, toward mass, toward the nodes. Galaxy clusters form at the intersections of filaments. That's where the nodes are, the places where multiple threads of the web converge. Clusters are the most massive bound structures in the universe. They contain hundreds to thousands of galaxies, all of them orbiting a common center of mass, held together by the combined gravity of the dark matter halos they sit inside. The largest clusters weigh more than 1 quadrillion times the mass of the Sun. That's 1,000 trillion, a 1 with 15 zeros after it. The Coma cluster, one of the largest nearby clusters, contains more than 1,000 galaxies and weighs roughly 10 to the power of 15 solar masses. The Virgo cluster, closer to home, is slightly smaller but still enormous, containing more than 1,000 galaxies spread across a region roughly 15 million light-years across. These clusters are still growing. They're accreting new matter as galaxies and gas continue to flow along the filaments and fall into the gravitational wells at the nodes. Clusters are not finished structures. They're active, dynamic, constantly pulling in more mass and merging with smaller clusters nearby. In a few billion years, many of the clusters we see today will have merged with their neighbors, forming even larger structures. The nodes of the cosmic web are getting denser. The scale of voids is hard to process because voids are defined by what's not there. A filament is something. You can point to it on a map. You can count the galaxies in it. You can measure its length and its mass. A void is nothing, or almost nothing. And trying to describe nothing at a scale of 100 million light-years requires a kind of mental gymnastics that doesn't come naturally. Imagine standing in the middle of a void. You can't, obviously, because there's nowhere to stand, but imagine it anyway. You're floating in space, somehow alive, somehow able to see. You look around. In every direction, for tens of millions of light-years, there is nothing. No galaxies, no stars, no glow of distant light, just darkness, pure, unbroken darkness. The nearest galaxy is 50 million light-years away, too faint and too far to see with the naked eye, even if you had perfect vision and infinite time to stare. You are alone in a way that no human has ever been alone. Not alone on a mountain or in a desert or on a distant island. Alone in a region of space so empty that light itself has almost nothing to interact with. The cosmic microwave background, the faint afterglow of the Big Bang, is still there, filling space with radiation, but it's so dim and so uniform that it wouldn't register as anything but a faint warmth, a background hiss that you'd only notice if you had instruments sensitive enough to detect it. You would be sitting in the most underdense region of the universe, surrounded by hundreds of millions of light-years of near-perfect vacuum, and the only thing keeping you company would be the occasional stray hydrogen atom drifting by every few minutes. Voids are not perfectly empty. That needs to be said clearly because the name is misleading. They contain gas, dark matter, and isolated galaxies. But the density is so low, the distribution so sparse, that calling them empty is not much of an exaggeration. The gas inside voids is ionized, blasted by radiation from distant galaxies and quasars, heated to temperatures of tens of thousands of degrees. It's too hot and too diffuse to collapse and form stars. The dark matter is there too, spread out in a thin web that mirrors the structure of the luminous cosmic web, but at much lower density. And the galaxies, the few that exist inside voids, are mostly small, irregular dwarfs, starved of the gas they'd need to grow larger, drifting through the emptiness with no neighbors and no future. Voids are where the universe gave up. They're the regions gravity couldn't organize, the places where the initial density was just slightly too low, and once matter started flowing out of them toward the filaments, there was nothing left to stop the process. The voids emptied, and they're still emptying. Every year, a little more gas gets pulled out of the voids and into the filaments. Every billion years, the voids grow a little larger, a little emptier, a little more like the true vacuum they're named after. The cosmic web was nicknamed by scientists in the early days of computational modeling. Before that, people called the structure the large-scale structure of the universe, which is accurate but clunky. The term cosmic web caught on because it's vivid. It captures the image immediately, a web. Threads and gaps, structure and emptiness. The metaphor works because it's not just visual, it's functional. A spider web is a tool. It's designed to catch things, to channel motion, to direct flow. The cosmic web does the same thing. It catches matter. It channels the motion of galaxies along filaments. It directs the flow of gas toward the nodes. The web is a machine built by gravity, and it's still running. It's still organizing the universe, and it will keep running until the expansion of space tears it apart. Gravitational lensing helped astronomers map the cosmic web, especially the dark matter parts. Gravitational lensing is a trick of light. When light from a distant galaxy passes near a massive object, the gravity of that object bends the light's path, just like a lens bends light in a pair of glasses. If the massive object is a galaxy cluster, the bending can be extreme, distorting the images of background galaxies into arcs and rings. By studying the amount of distortion, astronomers can calculate how much mass is sitting in the cluster and where that mass is distributed. Most of it turns out to be dark matter, and by mapping the lensing effects across large regions of space, astronomers can build a map of the dark matter distribution, tracing the filaments and nodes of the cosmic web even where no galaxies are visible. The technique is powerful. It's one of the few ways we have to see dark matter directly, or at least to see its effects directly, and it's confirmed what the simulations predicted. The cosmic web is real. The filaments are there. The voids are there. The pattern holds across the entire observable universe. The web's shape is not random. It's anisotropic, which means it's not the same in all directions. Some regions are more filamentary, others more clustered. The pattern varies depending on local conditions, on how the initial density fluctuations were distributed in a given region, on how matter has flowed and merged over billions of years. But the overall structure, the existence of filaments and voids and nodes, is consistent everywhere. The cosmic web is a universal feature. It's not unique to our part of the universe. It's not a local anomaly. It's how the universe is built. On the largest scales, matter organizes itself into this pattern because gravity, acting on an uneven distribution, always produces the same result. Overdense regions get denser, underdense regions get emptier, the rich get richer, the poor get poorer. And the result, after 13.8 billion years of gravitational evolution, is the cosmic web. The web stretches across the entire observable universe. That phrase, observable universe, is about to become very important because we're approaching the edge of what we can see, not the edge of what exists, the edge of what light has had time to reach. The cosmic web continues beyond the horizon, beyond the limit of our telescopes, out into regions we will never be able to observe because the light from those regions hasn't arrived yet and, thanks to the accelerating expansion of space, never will. But within the observable universe, within the bubble of space we can actually see, the cosmic web pervades everything. Every galaxy, every cluster, every supercluster, all of it is part of the web. Laniakea is a piece of the web. The Milky Way is a single point on a single filament in a single corner of the web, and the web itself is the largest coherent pattern of structures known. It is the top of the hierarchy, the final level of organization before you run out of universe to organize. The observable universe has a radius of about 46.5 billion light-years. That's the distance to the farthest objects we can theoretically see, the edge of the bubble. But the full diameter, edge to edge through the middle, is roughly 93 billion light-years. That's larger than it should be, larger than you'd expect from a universe that's only 13.8 billion years old. Light has only been traveling for 13.8 billion years, so how can the edge be 93 billion light-years away? The answer has to do with expansion, with the fact that space itself is stretching, carrying distant objects away from us faster than light can close the gap. The edge of the observable universe is not a wall, it's a horizon, a boundary defined not by what exists, but by what we can see. Beyond that horizon, the universe continues, the cosmic web continues, galaxies continue, filaments and voids and nodes continue, but we will never see them. The light from those regions will never reach us. And because of dark energy, because the expansion of space is accelerating, the horizon is not growing, it's shrinking. Galaxies that are visible today will disappear over the next tens of billions of years, redshifted into invisibility as space carries them beyond the edge of what we can observe. The observable universe is getting smaller. The cosmic web is dissolving at the edges, not because it's breaking apart, but because we're losing the ability to see it. That shrinking horizon, that edge of visibility, is the next step. It's where the scale stops being about distance and starts being about time, about how long light has been traveling, and why the universe's edge sits 93 billion light-years away when the universe itself is only 13.8 billion years old. The math doesn't seem to work until you understand what expansion means, what it does to space, and how it changes the rules. The cosmic web is the infrastructure, the skeleton, the largest pattern in existence. But even the web has limits, and those limits are defined by the observable horizon, the edge of everything we can see. The cosmic web is the largest structure in the universe. That's what we just established. Filaments and voids stretching across hundreds of millions of light-years, matter organized into a pattern so vast that galaxies are just pixels in the overall map. It's enormous, it's incomprehensible, and it's still not the edge, because the cosmic web, as large as it is, sits inside something even larger. A bubble, a horizon, a boundary defined not by structure or matter or gravity, but by time, by how long light has been traveling and how far it's managed to get. We call that boundary the observable universe, and it sits roughly 93 billion light-years away, edge to edge, diameter. The full width of everything we can theoretically see if we had perfect instruments and infinite patience and no dust or gas or anything else blocking the view. 93 billion light-years. That number is larger than anything we've talked about so far, larger than Laniakea, larger than the cosmic web, larger than any structure that exists. And the first thing your brain probably did when you read it was assume it was a mistake, because the universe is only 13.8 billion years old. Light has only been traveling for 13.8 billion years. So how can the edge be 93 billion light-years away? The math doesn't seem to work, and that's the uncomfortable part. The math does work. It just works in a way that breaks every intuition a human mind has about distance and time and how things are supposed to behave. The observable universe is not the universe. That sentence needs to sit for a moment, because most people hear the term and assume it's describing everything that exists. It's not. The observable universe is the part of the universe we can see, the part where light has had enough time to reach us since the Big Bang. Beyond that boundary, the universe continues. Galaxies, stars, planets, filaments, voids, all of it keeps going. We just can't see it. The light from those regions hasn't arrived yet. And because space is expanding, because the expansion is accelerating, the light from the farthest regions will never arrive. The observable universe is a bubble with Earth at the center. Not because Earth is special, not because we're sitting at some privileged location, but because the observable universe is defined by what we can observe, and we're the ones doing the observing. If you moved to a different galaxy and set up your telescopes there, you'd have a different observable universe, a different bubble, centered on your new location. Some of the galaxies you could see from there, we can't see from here. And some of the galaxies we can see, you wouldn't be able to see from there. The edges would be different. The bubble would overlap with ours, but not match it exactly. Every point in the universe has its own observable universe, its own horizon, its own bubble of visibility, and none of them are the whole thing. The edge of the observable universe sits roughly 46.5 billion light-years away. That's the radius, the distance from Earth to the horizon in any direction. Double it and you get the diameter, 93 billion light-years. Some sources round it to 92. Some push it to 94. The exact number depends on which measurements of the expansion rate you trust, and those measurements have error bars, but the order of magnitude is solid. We're talking about a sphere roughly 93 billion light-years across, with us sitting somewhere near the middle, and everything we've ever observed, every galaxy, every star, every photon that's ever hit a telescope came from inside that sphere. Outside it, we have no data, no observations, no evidence, just math and models and the assumption that the universe doesn't suddenly stop obeying the laws of physics once you cross an arbitrary line 46 billion light-years from Earth. That assumption is probably safe, but it's still an assumption. Here's the problem. Light travels at a fixed speed, roughly 300,000 kilometers per second in a vacuum. Nothing goes faster. Light sets the speed limit for information, for causality, for everything that can interact or communicate across space. If the universe is 13.8 billion years old, then light has been traveling for 13.8 billion years, and in that time it should have covered 13.8 billion light-years. That's the light travel distance, the maximum distance light could have moved in the time available. So the edge of the observable universe should be 13.8 billion light-years away, not 46. The diameter should be 27.6 billion light-years, not 93. And for decades, that's exactly what astronomers assumed. They assumed the size of the observable universe was just twice the age of the universe multiplied by the speed of light. Simple, clean, wrong. The mistake is thinking of space as static, as a fixed stage where objects move around, but the stage itself stays put. That's how space behaves on small scales, on human scales, on solar system scales, even on galactic scales. The distance between Earth and the Moon doesn't change because space is expanding. The Moon is orbiting us, held in place by gravity, and the expansion of space is so slow and so weak at that distance that gravity completely dominates. The same is true for the distance between the Sun and the nearest star. Space is expanding, technically, but the effect is negligible. Gravity and the random motions of stars through the galaxy are much stronger. The expansion only matters when you look at distances large enough that gravity can't hold things together. Distances between galaxy clusters, distances between superclusters, and especially distances to objects near the edge of the observable universe. At those scales, space is not static, it's stretching. And when space stretches, the objects embedded in it get carried along for the ride. Imagine drawing two dots on a deflated balloon with a marker. Measure the distance between them. Now inflate the balloon. The dots move apart, not because they're traveling across the surface of the balloon. They're not moving at all relative to the rubber they're sitting on. The surface itself is expanding, and the dots are just going along with it. The space between them is increasing, even though neither dot is moving through space. That's what's happening in the universe. Galaxies are the dots, space is the balloon, and the balloon has been inflating for 13.8 billion years. A galaxy that emitted light toward us shortly after the Big Bang was much closer when it emitted that light than it is now. The light has been traveling toward us the whole time, but while it was traveling, space was expanding. The galaxy moved farther away, not because it was flying through space, because space itself was stretching, carrying the galaxy with it. By the time the light reaches us, the galaxy that emitted it is much, much farther away than the light travel distance would suggest. Here's a concrete example. The cosmic microwave background is the oldest light we can see. It's the afterglow of the Big Bang, emitted roughly 380,000 years after the universe began. At that time, the universe was a hot, dense plasma of hydrogen and helium, and it was opaque. Light couldn't travel freely because it kept getting absorbed and re-emitted by the charged particles filling space. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. The plasma cleared, space became transparent, and the light that had been trapped in the plasma was suddenly free to travel. That light has been traveling ever since. It's been moving toward us for 13.8 billion years, give or take a few 100,000, and we can see it. Every telescope pointed at the sky picks it up. It's a faint microwave glow, uniformly distributed across the entire sky, with tiny temperature fluctuations that tell us about the density variations in the early universe. The light travel distance to the source of that light is about 13.8 billion light-years. But the source, the region of space that emitted the light, is not 13.8 billion light-years away. It's about 46 billion light-years away, because space has been expanding the entire time the light was traveling. The region that emitted the light has been carried away from us by the expansion, and it's now sitting near the current edge of the observable universe. This is not a trick. This is not a misunderstanding of the data. This is what happens when space expands. The comoving distance, the actual distance to an object right now, is larger than the light travel distance, the distance light has covered to get here. And the ratio between those two distances depends on how much space has expanded during the light's journey. In the early universe, space was expanding very quickly, much faster than it is today. For the first fraction of a second after the Big Bang, space expanded faster than the speed of light. That sounds like a violation of relativity. It's not. Relativity says nothing can move through space faster than light. It doesn't say anything about how fast space itself can expand. Space can stretch as fast as it wants. Objects embedded in that space are not moving, they're just being carried by the expansion. The distance between them is increasing faster than light, but neither object is actually traveling faster than light relative to its local surroundings. It's a subtle distinction, and it's one of the most commonly misunderstood aspects of cosmology, but it's critical. Because if space couldn't expand faster than light, the observable universe would be much smaller than it is. The current radius of the observable universe, 46.5 billion light-years, is a comoving distance. It's the distance to the edge right now, accounting for all the expansion that's happened since the light we're seeing was emitted. The light travel time is 13.8 billion years. The comoving distance is 46.5 billion light-years. The difference is expansion. Space stretched while the light was traveling, and the stretching added distance. If space had been static, if the universe had not been expanding, the edge would sit at 13.8 billion light-years. The diameter would be 27.6. But space did expand, and the result is a horizon that's nearly twice as far away as you'd naively expect. That expansion is still happening right now, as you're reading this. The universe is getting bigger, not the observable universe, that's actually getting smaller, in a sense we'll get to in a moment, but the actual universe, the full thing, is expanding. The distance between galaxy clusters is increasing. The distance between superclusters is increasing. The voids are getting larger. the filaments are stretching, and the rate of expansion, the speed at which space is growing, is accelerating. That acceleration is driven by something called dark energy, a mysterious force that seems to be pushing space apart. Dark energy makes up about 68% of the total energy density of the universe. Dark matter makes up about 27%. Normal matter, everything we can see and touch and build things out of, accounts for less than 5%. Dark energy is the dominant force in the cosmos, and it's causing the expansion to speed up. The farther away a galaxy is, the faster it's receding from us. Not because it's moving through space, because space itself is expanding between us and it. The expansion rate is measured by something called the Hubble constant. It tells you how fast space is expanding per unit distance. The current best estimate is somewhere around 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years you look outward, galaxies are moving away from you 70 kilometers per second faster. That might not sound like much. It's enough. At a distance of about 14 billion light-years, galaxies are receding from us at the speed of light. Beyond that distance, they're receding faster than light. Not because they're moving faster than light. Because space is expanding so quickly that the distance between us and them is growing faster than light can close the gap. And at the edge of the observable universe, at 46.5 billion light-years, the recession speed is about 3 times the speed of light. Light from those regions is still reaching us, but only barely. The light that was emitted long ago, when those regions were much closer, has had just enough time to make it here. But any light emitted from those regions today will never reach us. The expansion is too fast. The gap is widening faster than light can cross it. Those regions are beyond our cosmic event horizon, and we will never see them as they are now. We can only see them as they were billions of years ago, when they were closer. This introduces a concept called look-back time. When you look at a distant object, you're not seeing it as it is now, you're seeing it as it was when the light you're seeing left it. The farther away the object is, the longer ago that was. Look at the sun, and you're seeing it as it was about 8 minutes ago, because that's how long it takes light to travel from the sun to Earth. Look at the nearest star, Proxima Centauri, and you're seeing it as it was about 4 years ago. Look at Andromeda, and you're seeing it as it was 2.5 million years ago. Look at a galaxy 10 billion light-years away, and you're seeing it as it was 10 billion years ago, back when the universe was less than 4 billion years old. The farther you look, the further back in time you see. Telescopes are time machines. They don't take you to the past. They just show it to you. Every photon that hits your eye, or your camera, or your detector is a messenger from an earlier era, carrying information about what things were like when it began its journey. And the farthest photons, the ones coming from near the edge of the observable universe, are messengers from the earliest moments of cosmic history. The cosmic microwave background, that faint glow we talked about earlier, is the oldest light we can see. It's coming from a distance of about 46 billion light-years, but the light travel time is 13.8 billion years. The look-back time is nearly the full age of the universe. When you look at the cosmic microwave background, you're seeing the universe as it was 380,000 years after the Big Bang, before stars, before galaxies, before anything had time to collapse and ignite. Just a hot uniform plasma slowly cooling, about to become transparent for the first time. That light has been traveling ever since, stretched by the expansion of space from visible light into microwaves, its wavelength pulled longer and longer as space itself expanded. By the time it reaches us, it's been redshifted into the microwave part of the spectrum, too long a wavelength for the human eye to detect, but perfectly visible to radio telescopes. That light is the edge of what we can observe. Beyond the cosmic microwave background, the universe was opaque. Light couldn't travel freely. There's nothing to see. The cosmic microwave background is our horizon, the wall at the edge of the observable universe, not because the universe ends there, because the light ends there. Before that moment, there was no light that could reach us. After that moment, there was. And everything we can see, every star, every galaxy, every structure, formed after that wall of light. The total mass of ordinary matter in the observable universe is estimated at about 1.5 times 10 to the power of 53 kilograms. That's a 1 followed by 53 zeros. It's a number so large that it stops having any meaning. For comparison, the Earth weighs about 6 times 10 to the power of 24 kilograms. The Sun weighs about 2 times 10 to the power of 30 kilograms. The Milky Way, including all its stars and gas and dark matter, weighs about 1.5 times 10 to the power of 42 kilograms. The observable universe contains enough ordinary matter to make about 10 trillion galaxies the size of the Milky Way. That's just the ordinary matter, the stuff we can see. Add in dark matter, and the total mass goes up by a factor of about 5 or 6. Add in dark energy, which doesn't have mass in the usual sense but contributes to the total energy density of the universe, and the numbers get even larger. The observable universe is not empty, it's full, packed with matter and energy and structure. And all of it, every last atom, every photon, every particle, sits inside a sphere 93 billion light-years across. The size of the observable universe is not a guess, it's not a rough estimate, it's a calculation based on measured quantities. The age of the universe, the expansion rate, the density of matter, the density of dark energy. All of those numbers have been measured to high precision using a variety of independent methods. Supernovae, galaxy clustering, the cosmic microwave background, primordial light element ratios, all of them point to the same cosmological model, the same set of parameters. And when you plug those parameters into the equations that describe how the universe evolves, equations called the Friedmann equations, you get a prediction for the size of the observable universe, 93 billion light-years across. The number could vary by a few percent, depending on exactly which measurements you trust, but the order of magnitude is solid. This is not speculative. This is not theory in the sense of a guess. This is tested, confirmed, cross-checked physics. The observable universe is 93 billion light-years wide because the math says so and the observations agree. Here's the twist. The observable universe is shrinking, not in size. The radius is still 46.5 billion light-years, but in content. Galaxies at the edge are disappearing. Not because they're being destroyed, because the expansion of space is carrying them away faster than light, and the light they're emitting now will never reach us. Every year, galaxies cross the cosmic event horizon, the boundary beyond which we can never see them again. The event horizon sits at about 16 billion light-years. Any galaxy farther than that is already lost. We can see it as it was in the past, because the light from its past has had time to reach us. But we will never see what it looks like now. We will never receive any signal from it that was emitted after a certain point in its history. And as time goes on, more and more galaxies will cross that boundary. In a few tens of billions of years, the only galaxies we'll be able to see are the ones in our immediate neighborhood, the local group, maybe the Virgo cluster. Everything else will have been carried beyond the horizon by the accelerating expansion. The observable universe will still exist. It will still have a radius of 46.5 billion light-years, maybe larger, But it will be empty, almost no galaxies, almost no structure, just a few nearby objects drifting in a vast dark expanse, surrounded by the faint glow of the cosmic microwave background. That's the far future, the heat death, the long, slow fade. The universe won't end. It will just empty out, leaving us alone in the dark with no memory of what used to be out there. For now, though, the observable universe is full. It contains structure, light, motion, history. It contains the cosmic web, the superclusters, the galaxies. It contains the story of the past 13.8 billion years, written in light, encoded in the positions and motions and spectra of trillions of objects scattered across space. And we're just starting to read it. The James Webb Space Telescope, launched in late 2021, is designed to see farther than any telescope before it, to look deeper into the past, closer to the edge of the observable universe, to the moments just after the first stars ignited and the first galaxies began to form. Webb is not looking at distant objects because they're far away. It's looking at them because they're old, because the light from them has been traveling for so long that it carries information about an era we can't access any other way. Webb is a time machine, and what it's finding in the farthest reaches of the observable universe, in the earliest moments after the cosmic dark ages ended, is not what anyone expected. Galaxies that are too bright, too massive, too organized. Galaxies that shouldn't exist yet, sitting there fully formed, shining back at us from an era when the universe was supposed to still be figuring itself out. Those galaxies are the subject of the next part of this story. They're sitting near the edge of the observable universe, near the horizon, at distances so vast that the light we're seeing left them more than 13 billion years ago. And they're changing everything we thought we knew about how the universe grew up. The James Webb Space Telescope should not work. That might sound dramatic, but consider what it's actually doing. It's sitting 1.5 million kilometers from Earth, orbiting nothing, floating at a point in space where the gravitational pull of the Sun and the Earth balance out just enough to let it drift there indefinitely. It's staring at patches of sky so dark that Hubble couldn't find anything in them, and it's detecting light that has been traveling for more than 13 billion years, light so faint and so stretched by the expansion of space that by the time it arrives, it's barely a whisper. The telescope is colder than liquid nitrogen, shielded from the sun by a 5-layer sunshield the size of a tennis court, folded and unfolded in space like a piece of origami built by a species that refuses to accept the word impossible. And it works, not just works. It works better than anyone predicted. It's finding galaxies that shouldn't exist, stars that formed too early, structures that assembled too quickly. It's rewriting the early history of the universe, one observation at a time. And the reason it can do any of this comes down to 3 things: size, location, and infrared. Webb launched on Christmas Day 2021 from French Guiana, strapped to the top of an Ariane 5 rocket. The launch was perfect. The deployment was not guaranteed. The telescope was too large to fit inside any rocket fairing in one piece, so NASA folded it. The mirrors folded, the sunshield folded. The entire structure was packed into a space barely large enough to hold it, and the whole thing had to unfold in space, step by step, piece by piece, over the course of 2 weeks. 344 single points of failure. That's the number engineers calculated. 344 things that had to work correctly, in sequence, with no chance of sending anyone up to fix it if something went wrong. The stakes were absurd. The telescope cost $10 billion and took more than 20 years to build. If any one of those 344 steps failed, the entire mission would be over before it started. On January 8, 2022, the primary mirror finished unfolding. 18 hexagonal segments, each coated in a microscopically thin layer of gold, clicked into place and locked. The telescope was whole. On January 24th, it reached its final parking spot, a gravitational balance point called L2, roughly 4 times farther from Earth than the Moon. And on July 11th, 2022, after months of alignment and calibration, NASA released the first full-color images. The world saw them and assumed they were edited, enhanced, exaggerated for effect. They weren't. That's just what Webb can see. The primary mirror is 6.5 meters across. That's 21 feet, roughly 3 times the diameter of Hubble's mirror. But diameter doesn't tell the whole story. Light gathering power scales with area, and Webb's mirror has about 6 times the collecting area of Hubble's. More area means more light. More light means fainter objects become visible. Webb can detect objects 100 times fainter than Hubble's limit. 100 times. That difference, that single factor of 100, is the gap between seeing a nearby galaxy and seeing the first galaxies that ever formed. It's the difference between looking at the recent past and looking at the earliest moments of cosmic history, back when the universe was still an infant, still figuring out how to build things, still lighting its first stars. Hubble changed astronomy. That's not an exaggeration. Before Hubble, we didn't know the exact age of the universe. We didn't know how fast it was expanding. We didn't know if the expansion was slowing down or speeding up. Hubble measured the distances to distant supernovae and discovered that the universe's expansion is accelerating, driven by something we now call dark energy. That discovery won a Nobel Prize. Hubble found planets around other stars. It mapped the distribution of dark matter by observing gravitational lensing. It took deep field images, staring at tiny patches of seemingly empty sky for days at a time, and found thousands of galaxies in regions where ground-based telescopes saw nothing. Hubble proved that almost every point in the sky, no matter how dark it looks, is full of galaxies. Hubble was revolutionary, and Webb makes Hubble look like a toy. The reason is infrared. Hubble observes mostly invisible light, the same wavelengths the human eye can see, with some capability in ultraviolet and near-infrared. Webb observes in infrared, wavelengths longer than visible light, ranging from about 0.6 microns, which is just barely into the red, all the way out to 28 microns, deep in the mid-infrared. That shift in wavelength changes everything. Because the farther away a galaxy is, the more its light has been stretched by the expansion of space. A galaxy that emits ultraviolet light, the kind produced by young hot stars, will have that light redshifted into visible wavelengths if it's a few billion light-years away. Push it farther, 10 billion light-years, and the light shifts into the near-infrared. Push it all the way to the edge of the observable universe, 13 billion light-years or more, and the light that started as ultraviolet arrives as deep infrared. Hubble can't see it. The wavelength is too long. The light passes right through Hubble's instruments without registering. Webb was built specifically to catch that light. It's a time machine designed to see the universe as it was in the first few 100 million years after the Big Bang, the era when the first stars ignited and the first galaxies began to form. And it's doing exactly that. Webb's location matters as much as its design. It doesn't orbit Earth. It orbits the Sun, parked at a point called the second Lagrange point, L2 for short. Lagrange points are places in space where the gravitational pull of two large objects, in this case the Sun and the Earth, balance out in a way that lets a smaller object sit there without drifting. There are 5 of them scattered around the Earth-Sun system. L2 sits about 1.5 million kilometers from Earth, roughly 4 times the distance to the Moon, on the side of Earth facing away from the Sun. From that position, the Sun, Earth and Moon all sit in the same direction. That's critical because Webb needs to stay cold. Infrared detectors are heat sensors. If the telescope itself is warm, it will glow in infrared and drown out the faint signals it's trying to detect. So Webb is shielded. A massive sun shield, 5 layers of material each thinner than a human hair, sits between the telescope and the Sun. The sun shield is the size of a tennis court, roughly 70 feet by 46 feet, and it blocks the Sun's heat so effectively that the difference in temperature between the Sun-facing side and the telescope side is more than 300 degrees Celsius. The side facing the Sun bakes at about 85 degrees Celsius. The side facing the telescope sits below -230 degrees Celsius. Cold enough that Webb's instruments operate at temperatures colder than Pluto's surface. Cold enough that if you somehow stood next to it, you would freeze solid in seconds. That cold is not optional, it's required. Without it, Webb couldn't see the faintest infrared signals coming from the edge of the universe. The telescope has 4 main instruments, each one designed for a specific job. The Near-Infrared Camera, NIRCam, is Webb's primary imager. It takes pictures, beautiful, high-resolution pictures of galaxies, stars, nebulae, anything that emits infrared light. NIRCam was the instrument responsible for the first deep-field images released in July 2022, the ones that made everyone stop and stare because they showed galaxies in a clarity and detail that had never been achieved before. The Near-Infrared Spectrograph, NIR-SPEC, splits light into its component wavelengths, producing spectra that tell you what an object is made of, how hot it is, how fast it's moving, whether it contains oxygen or carbon or hydrogen. The mid-infrared instrument, MIRI, observes at longer wavelengths, deeper into the infrared, seeing through dust clouds that block visible light and revealing the hidden regions where stars are being born. And the fine guidance sensor, which includes something called NIRIS, keeps the telescope locked onto its target with precision so extreme that Webb can hold its gaze steady to within 17 milliarseconds. That's the width of a human hair seen from a kilometer away. That precision is what lets Webb stare at a single patch of sky for hours, collecting every last photon, building up images of objects so faint that they're invisible to every other telescope humanity has ever built. Webb's first major science goal was to see the first light in the universe, not the cosmic microwave background. That's the oldest light we can observe, but it's not light from stars. It's light from the hot plasma that filled the universe 380,000 years after the Big Bang. The first stars came later, somewhere between 100 and 250 million years after the Big Bang. That era is called the Cosmic Dark Ages, and it's dark because there were no stars yet. Just clouds of hydrogen and helium drifting through space, slowly collapsing under their own gravity, heating up, compressing, until finally, somewhere, the first star ignited, then another, then thousands, then millions. Those first stars were massive, hot, short-lived. They burned hydrogen into helium, helium into carbon, carbon into oxygen, building heavier elements in their cores. And when they exploded, they seeded the surrounding gas with those elements, enriching the universe with the raw materials needed to build the next generation of stars. From those enriched clouds, the first galaxies assembled. Small, irregular, chaotic collections of stars, nothing like the grand spirals and ellipticals we see today, just clumps. But they were the beginning, and Webb was built to find them. In its first year of operation, Webb found galaxies sitting at redshifts higher than anyone expected. Redshift is the measure of how much a galaxy's light has been stretched by the expansion of space. The higher the redshift, the farther away the galaxy is, and the earlier in the universe's history we're seeing it. Hubble's record for the most distant confirmed galaxy sat at a redshift of about 11, corresponding to a time roughly 400 million years after the Big Bang. Webb shattered that record within months. It found galaxies at redshift 13, 14, even candidates pushing past redshift 20. One galaxy, designated JWST 14-0, was observed as it existed roughly 290 million years after the Big Bang. 290 million years, that's less than 2% of the current age of the universe. The light from that galaxy has been traveling for more than 13 billion years. When it left, the universe was a fraction of its current size. Earth didn't exist. The Sun didn't exist. The Milky Way was still assembling itself from smaller fragments. And this galaxy, this tiny collection of stars sitting near the edge of everything we can see, was already there, already formed, already shining. Here's the problem. That galaxy shouldn't exist. Not at that distance, not at that time. The standard model of galaxy formation predicts that the first galaxies should be small, dim, irregular, proto-galaxies, baby galaxies, collections of a few million stars at most, struggling to hold themselves together, barely distinguishable from the chaotic background of the early universe. But the galaxies Webb is finding are not small, they're not dim. Some of them are massive, containing hundreds of millions of stars, maybe billions. Some of them are bright, shining with the light of hot young stars, forming at rates that shouldn't be possible so early. And some of them show structure. Not the clean spiral arms or smooth elliptical shapes of mature galaxies, but structure nonetheless, clumps, cores, concentrations of mass that suggest they've already undergone significant evolution. These galaxies have had time to grow, time to build, time to settle into something approaching stability. But the universe was only a few 100 million years old when the light we're seeing left them. There wasn't enough time, not according to the models. Not according to everything astronomers thought they understood about how galaxies form. The detection of oxygen in some of these early galaxies made the problem worse. Oxygen doesn't exist in the primordial universe. It has to be made inside stars, fused from lighter elements in the cores of massive suns, and then scattered into space when those stars explode. Finding oxygen in a galaxy that we're seeing less than 300 million years after the Big Bang means stars had already been born, lived their lives, and died by that point. All within a time window that, by previous estimates, wasn't long enough for even the first generation of stars to finish forming. The timeline doesn't fit, the observations don't match the theory, and astronomers are now in the uncomfortable position of having to either revise the models, which they've spent decades refining, or accept that something about the early universe was fundamentally different from what they assumed. Maybe star formation was faster. Maybe the first stars were more efficient at enriching their surroundings. Maybe dark matter behaved differently in the early universe, clumping together more aggressively and pulling normal matter into galaxies at a rate current simulations don't account for. Nobody knows. The data is clear, the explanation is not. Webb's deep field images are haunting. Not because they're dark or empty, but because they're not. Point Webb at a patch of sky the size of a grain of sand held at arm's length. a region so small that to the naked eye it looks like pure black, and Webb finds galaxies, thousands of them, stacked on top of each other in layers, some close, some distant, some so far away that their light has been traveling since the universe was young. Every bright point in those images is a galaxy, every smudge, every arc and ring caused by gravitational lensing, where the light from a distant galaxy is bent and distorted by the gravity of a massive cluster sitting between it and us. The images don't feel crowded, they feel full. There is no empty space, there is no blank canvas. Just galaxies everywhere, at every distance, stretching all the way back to the edge of the observable universe. And each one of those galaxies contains billions of stars. Each star might have planets. Each planet might have a history. The scale stops being about numbers and starts being about the sheer density of existence. The universe is not sparse, it's packed. The reionization epoch is one of Webb's primary targets. That's the period in cosmic history when the first stars and galaxies ionized the neutral hydrogen filling the universe, clearing the fog and making space transparent again. Before reionization, the universe was opaque. Light couldn't travel freely because it kept getting absorbed by neutral hydrogen atoms. After reionization, space became transparent. Light could travel unimpeded. The transition didn't happen all at once. It happened gradually, over hundreds of millions of years, as more and more stars formed and more ultraviolet radiation flooded into the surrounding gas, ionizing it bit by bit. By the time the universe was about 1 billion years old, reionization was complete. The fog had lifted. And Webb is seeing galaxies from both sides of that transition. Galaxies caught in the act of clearing the fog, their light piercing through the last patches of neutral hydrogen. Those observations will help astronomers pin down exactly when reionization happened, how fast it happened, and which galaxies contributed the most to the process. It's one of the last major gaps in the timeline of the universe's evolution, and Webb is closing it. Webb is not working alone. In July 2023, the European Space Agency launched another telescope called Euclid. Euclid's job is not to look deep, it's to look wide. While Webb focuses on tiny patches of sky and goes as deep as possible, Euclid is mapping the large-scale structure of the universe across a huge area. Over 6 years, Euclid will survey about 1/3 of the entire sky, measuring the positions and shapes of billions of galaxies. The goal is to trace the cosmic web in unprecedented detail, mapping how galaxies cluster along filaments, how voids are distributed, how the structure has evolved over the past 10 billion years. Euclid will also study dark energy by measuring how the expansion of space has changed over time. By looking at how galaxies are distributed at different distances, and therefore at different points in cosmic history, Euclid can track the rate of expansion and see how dark energy has influenced it. The data will complement Webb's deep observations, providing the wide-field context that shows how the galaxies Webb is studying fit into the larger structure. There's a strange tension in astronomy right now between what the models predict and what the observations show. The models, refined over decades, are based on solid physics, general relativity, the standard model of particle physics. The equations that describe how matter collapses under gravity and how stars form and how galaxies grow. Those models work. They explain the cosmic microwave background. They explain the distribution of galaxies in the nearby universe. They explain the abundances of light elements like hydrogen and helium. But they struggle to explain what Webb is seeing at high redshifts. The galaxies are too big, too bright, too mature. The black holes sitting at their centers are too massive. The star formation rates are too high. It's not that the observations are wrong. The data is clear. The redshifts have been confirmed, the distances have been checked. It's that the models, as good as they are missing something. Either the early universe was more efficient at forming stars than anyone thought, or the conditions were different in ways the simulations don't capture. Or the models are wrong, not completely wrong. Just wrong enough that the predictions they make for the first few 100 million years of cosmic history don't match reality. That's not a failure, that's science. You build a model, you test it, the data tells you where it breaks, and then you fix it. But the process is uncomfortable, especially when the model in question has been the foundation of cosmology for the better part of a century. Webb's ability to observe in infrared also lets it see through dust. Visible light gets blocked by dust clouds, the same clouds where new stars are forming. Hubble can see the edges of those clouds, the bright regions where light is escaping, but it can't see inside. Webb can. Because infrared light has a longer wavelength, it passes through dust more easily, like the way radio waves pass through walls. MIRI, the mid-infrared instrument, is particularly good at this. It's peering into stellar nurseries, regions where gas clouds are collapsing and fragmenting into clumps that will become stars. It's watching planets form, seeing the disks of gas and dust swirling around young stars, the raw material from which solar systems are built. It's even detecting organic molecules, complex carbon-based compounds, in those disks. Not life, not anything close to life, but the building blocks, the ingredients, the stuff that, given enough time and the right conditions, might eventually lead to something more. Webb is showing us the universe in its infancy and the universe in the process of creating new worlds, both at the same time. It's a telescope designed to answer two of the oldest questions humans have ever asked. Where did we come from, and are we alone? The most distant objects Webb has detected are sitting near the edge of the observable universe, not quite at the edge. That boundary, the cosmic microwave background, is still the farthest thing we can see, but Webb is getting close. The galaxies it's finding at redshift 1415, maybe higher, existed less than 300 million years after the Big Bang. The light from them has been traveling for 13.5 billion years, give or take. The galaxies themselves, the actual structures as they exist right now, are much farther away. They've been carried by the expansion of space to distances approaching 46 billion light-years, but we'll never see them as they are now. The light they're emitting today will never reach us. The expansion is too fast. The gap is widening faster than light can close it. What we're seeing is ancient history, a snapshot of a galaxy frozen in time, preserved in the light that left it when the universe was still a toddler. And that galaxy, wherever it is now, however it's evolved, is forever beyond our reach. Webb's mission was designed to last 5 to 10 years. The limiting factor is fuel. The telescope uses thrusters to make tiny adjustments to its orbit, keeping it parked at L2. Those thrusters run on hydrazine, and once the fuel is gone, the telescope will drift. It won't fall back to Earth. It's too far out for Earth's gravity to pull it back. It will just drift away, slowly spiraling out of its stable position, and eventually it will lose the ability to keep its instruments pointed at targets. The mission will end not because the telescope breaks, but because it runs out of gas. Engineers were conservative with the fuel estimates. The launch was so precise, the trajectory so perfect, that Webb used less fuel than expected during its journey to L2. That means it might last longer than 10 years, maybe 15, maybe 20, nobody knows for sure. But eventually it will stop working. And when it does, it will drift through space, silent and cold, carrying with it the gold-coated mirrors that once stared at the edge of the universe and brought back images of creation. For now, Webb is working. It's observing. It's collecting data. Every week, new images are released. New discoveries announced. Galaxies that didn't exist in any catalogue a year ago are now pinned down, measured, analyzed. The early universe is coming into focus, not as a vague theoretical model, but as a real place with real objects, each one unique, each one carrying information about what happened in the first few 100 million years after the Big Bang. And every new observation raises more questions than it answers. That's not frustrating. That's the point. Science doesn't end when you find an answer. It ends when you stop asking questions. Webb is giving astronomers more questions than they know what to do with. That's success. That's progress. That's exactly what a $10 billion telescope sitting 1.5 million kilometers from Earth, staring at the faintest light in the universe, is supposed to do. The observable universe, that 93 billion light-year wide bubble we talked about in the last chapter, is not a static photograph. It's a living archive. Every galaxy, every star, every photon carries a piece of the story. Webb is reading that story, line by line, pushing farther and farther back toward the beginning. And what it's finding is not a simple, orderly progression from simple to complex. It's finding complexity early, structure early, galaxies and stars and black holes appearing faster than the models said they could. The universe, it turns out, didn't waste time. It got to work immediately. And we're only just now, 13.8 billion years later, starting to see what it built in those first few 100 million years. The light is still arriving. The data is still pouring in. And the edge of the observable universe, that horizon sitting 46.5 billion light-years away, is still out there, waiting. But even that edge is not the edge. The universe doesn't stop at the horizon. It keeps going. And the question of how far it goes, how much more there is beyond what we can see, is the next step. The one that takes us past observation and into theory, past measurement and into mathematics, past the edge of what we can see and into the realm of what we can only imagine. The observable universe is enormous, but it's just a bubble, a tiny fraction of something vastly, incomprehensibly larger. And that larger thing, the true scale of the universe, is what comes next. The observable universe is not the universe. We've said that before, but it needs to be said again because the distinction matters more than almost anything else we've talked about so far. The observable universe, that 93 billion light-year wide bubble with us sitting somewhere near the middle, is just the part we can see. The part where light has had enough time to reach us since the Big Bang. Beyond that boundary, the universe continues. It doesn't stop. It doesn't end. It doesn't hit a wall or fade into nothingness. It just keeps going. Galaxies, stars, planets, filaments, voids, the cosmic web, all of it stretches outward past the horizon, past the edge of what we can observe, into regions we will never see. And the question of how far it goes, how much more there is beyond the bubble, is not a question we can answer with telescopes. It's a question we have to answer with math, with theory, with models that extrapolate from what we can measure to what we can only imagine. And the answer, depending on which model you trust, ranges from a lot more to infinitely more. Neither option is comforting. Start with what we know. The observable universe has a radius of about 46.5 billion light-years. That's the comoving distance to the edge, the actual distance right now, accounting for all the expansion that's happened since the light we're seeing was emitted. The diameter is 93 billion light-years. The volume is enormous. Plug the numbers into the formula for the volume of a sphere, and you get roughly 4 × 10⁻⁸ cubic light-years. That's a 4 with 80 zeros after it. Inside that volume, there are an estimated 2 trillion galaxies, maybe more. Each galaxy contains anywhere from a few million to a few trillion stars. Add it all up, and you get roughly 10 to the power of 24 stars in the observable universe. That's a trillion, a 1 with 24 zeros. Every one of those stars might have planets. Some of those planets might be in the habitable zone, the region where liquid water could exist on the surface. Some of those planets might have life. We don't know. We can't check. But the numbers suggest that if life is possible, if it's not some bizarre fluke unique to Earth, then it's almost certainly out there, somewhere, in one of those 2 trillion galaxies, orbiting one of those trillion stars. And the observable universe, enormous as it is, packed with galaxies and stars and worlds we'll never see, is just a bubble, a tiny fraction of the whole. Here's why we think that. The observable universe is defined by a horizon, a boundary set by the speed of light and the age of the universe. Light has been traveling for 13.8 billion years, give or take, and accounting for the expansion of space during that time, the farthest light has managed to reach us from is about 46.5 billion light-years away. That's our horizon. But there's no reason to think the universe stops at that distance. No physical law says the universe has to end where our ability to observe it ends. The horizon is not an edge, it's a limit of visibility, like standing on a hilltop and looking out at the landscape. You can see to the horizon, a few miles in every direction, and beyond that horizon, the land keeps going. You just can't see it from where you're standing. The observable universe is the same. We can see to a distance of 46.5 billion light-years. Beyond that, the universe continues. We just can't see it, and we never will. Because the expansion of space is accelerating, driven by dark energy, and the light from regions beyond the current horizon will never have time to reach us. The gap is widening faster than light can close it. The horizon is shrinking, not expanding. Every year, galaxies at the edge are disappearing from view, redshifted into invisibility as space carries them away. The observable universe is getting smaller in content, even as the actual universe, the full thing, continues to expand. So how much more is there? How much universe sits beyond the horizon? The honest answer is, we don't know. We can't measure it. We can't observe it. We can only infer it from the properties of the part we can see, and those properties point to a universe that is vastly, incomprehensibly larger than the observable portion. The first clue comes from the shape of space itself. General relativity, Einstein's theory of gravity, describes space as a fabric that can bend and curve in response to mass and energy. The overall shape of the universe, the geometry of space on the largest scales, depends on the total density of matter and energy. If the density is high enough, space curves back on itself, forming a closed universe, a shape like the surface of a sphere. In a closed universe, if you traveled far enough in one direction, you'd eventually loop around and come back to where you started. If the density is lower, space curves outward, forming an open universe, a shape like the surface of a saddle. In an open universe, space stretches infinitely in all directions, and if the density is exactly right, sitting at a critical value, space is flat. Not flat like a piece of paper. Flat in the sense that parallel lines stay parallel forever, that the angles of a triangle add up to exactly 180 degrees, that the geometry is Euclidean. A flat universe also extends infinitely in all directions. It has no edge, no boundary, no center, just space, going on forever. Measurements of the cosmic microwave background, the afterglow of the Big Bang, have been used to measure the curvature of space with extraordinary precision. The results, published by the Planck satellite and confirmed by other surveys, show that the universe is flat, or at least very close to flat. The curvature, if it exists at all, is so small that it's undetectable within the current margin of error. That flatness is not an accident. It's predicted by a theory called cosmic inflation, which describes what happened in the first fraction of a second after the Big Bang. Inflation proposes that space expanded exponentially fast during a brief period, faster than the speed of light, faster than anything, stretching from a region smaller than an atom to something cosmically large in a tiny fraction of a second. That expansion smoothed out any curvature that might have existed, flattening space the way inflating a balloon smooths out wrinkles on its surface. By the time inflation ended, the universe was flat, and it stayed flat ever since, at least on the scales we can measure. Here's where the numbers get uncomfortable. If the universe is truly flat, not just approximately flat, but exactly flat, then it's infinite. It has no edge. It goes on forever. Every direction you look, space continues without end. Galaxies, stars, planets, all of it stretches outward infinitely, filling an infinite volume with an infinite amount of matter. The observable universe, that 93 billion light-year-wide bubble, would be an infinitesimally small patch of an infinite whole. Not a small patch, infinitesimally small, 0%, a single point in an endless expanse. And every other observable universe, the bubble you'd see if you moved to a different location, would also be infinitesimally small. The total universe would be so large that the word large stops having meaning. Infinity is not a number, it's a concept, a description of something that has no limit. And if the universe is infinite, then everything we've talked about so far, every galaxy, every supercluster, every filament in the cosmic web, all of it is just a rounding error in the accounting of existence. Most physicists don't like infinity. It's uncomfortable, it's hard to test. It breaks a lot of the intuitions that make physics work. But the math doesn't care what physicists like. If the curvature of space is zero, if the universe is flat, then the universe is infinite. There's no way around it. The only alternative is that the universe is so large that the curvature is too small to measure, but still present. In that case, the universe would be finite but unimaginably vast. One study, published in the early 2000s, looked at the constraints on curvature from the cosmic microwave background and calculated that if the universe is closed, if it curves back on itself, the minimum radius would have to be at least 150 times the radius of the observable universe. That's a minimum, the lower bound, the smallest the universe could possibly be and still match the observations. 150 times 46.5 billion light-years is roughly 7 trillion light-years. The diameter would be about 14 trillion light-years. That's the minimum size of a closed universe. The actual size could be much, much larger. And even that minimum is so vast that it makes the observable universe look like a speck. Inflation makes the problem worse. During the inflationary period, space expanded by a factor of at least 10 to the power of 26. Some models push that factor higher, 10 to the power of 50 or more. That means the universe grew by a factor of a trillion in less than a trillionth of a second. The region of space that became our observable universe was once smaller than an atom, and that tiny region expanded into something cosmically large. But inflation didn't just affect our patch of space, it affected the entire universe. Every region, near and far, expanded by the same factor. If the universe was already large before inflation, it became incomprehensibly larger after. If it was infinite before inflation, it stayed infinite. But if it was finite, the expansion stretched it so far that the total size dwarfs anything we can observe. One estimate, based on the assumption that inflation occurred at close to the speed of light, suggests the total universe could be 10 to the power of 23 times larger than the observable universe. That's a 1 with 23 zeros. The observable universe, in that scenario, would be less than 1 part in a trillion of the whole, less than 0.000000000001%. You'd need more zeros than fit on this page to write it out. Another way to think about it comes from the statistics of the cosmic microwave background. The temperature fluctuations in the CMB, those tiny hot and cold spots that tell us about the density variations in the early universe, have been measured in exquisite detail. The pattern of fluctuations depends on the size of the universe. If the universe were small, comparable to the size of the observable universe, we'd see correlations on very large scales, patterns that repeat across the sky. We don't see those patterns. The CMB looks statistically random on the largest scales, which suggests the universe is much larger than the region we can observe. A study published in the journal Physical Review used this reasoning to estimate that the universe is at least 250 times larger than the observable universe. That's another lower bound, another minimum. The actual size could be thousands of times larger, millions, billions. There's no upper limit. The data only rules out universes that are too small. It doesn't constrain how large the universe can be. The cosmic microwave background is the edge of the observable universe in a very literal sense. It's the farthest thing we can see. The light from the CMB was emitted roughly 380,000 years after the Big Bang, when the universe cooled enough for neutral hydrogen to form and space became transparent for the first time. That light has been traveling ever since, stretched by the expansion of space from visible light into microwaves, and it's still arriving. Every telescope pointed at the sky picks it up, a faint uniform glow coming from every direction. The CMB marks the boundary between the transparent universe and the opaque plasma that came before it. Before the CMB, light couldn't travel freely. The universe was a fog. After the CMB, space cleared and light could propagate. That transition, that moment when the universe became transparent, is the edge of what we can observe. Not because the universe ends there, because the light ends there. Beyond the CMB, the universe was opaque. There's nothing to see. No stars had formed yet, no galaxies, no structure. Just hot, dense plasma cooling and expanding. And beyond that plasma, farther back in time, closer to the Big Bang itself, the physics gets murky. The temperatures and densities were so extreme that our current theories start to break down. General relativity and quantum mechanics, the two pillars of modern physics, don't play well together at those scales. Nobody knows exactly what happened in the first fraction of a second after the Big Bang, because we don't have a theory of quantum gravity that works. The CMB is the edge of what we can see and the edge of what we understand. Past that, it's theory, speculation, educated guesses. If the universe is infinite, then it contains infinite matter, infinite galaxies, infinite stars, infinite planets. And if matter is distributed the same way everywhere, if the laws of physics are the same in every region, then every possible configuration of matter exists somewhere. Not just likely configurations, every configuration, including exact copies of you, of Earth, of the Milky Way. In an infinite universe, there are infinitely many regions identical to our observable universe. Infinitely many Earths where someone who looks exactly like you is reading this exact sentence at this exact moment. infinitely many where they stopped reading halfway through, infinitely many where Earth never formed, infinitely many where life never evolved. The math is straightforward. If you have infinite trials and a finite number of possible outcomes, every outcome occurs infinitely many times. The argument makes physicists uncomfortable because it's not testable. You can't prove it. You can't observe those other regions. They're beyond the horizon, forever out of reach. But the logic is sound. If the universe is infinite and the laws of physics are the same everywhere, then everything that can happen does happen, somewhere, infinitely many times. Most cosmologists accept that the universe extends far beyond the observable region. The debate is not whether there's more, the debate is how much more, and whether it's finite or infinite. The data we have, the measurements of the CMB, the observations of large-scale structure, the constraints on curvature, all point to a universe that is either infinite or so large that the difference doesn't matter. Either way, the observable universe is a tiny fraction of the whole, less than 1%, possibly far less. One study concluded that the observable universe represents less than 0.0001% of the total volume. Another suggested it could be as low as 1 part in a trillion. The exact number depends on assumptions about inflation, about the shape of space, about how long the universe has been expanding. But every estimate agrees on one thing: the observable universe is minuscule compared to what lies beyond. That changes the meaning of everything. Every discovery, every observation, every catalogue of galaxies and clusters and superclusters, all of it is local. A map of our immediate neighborhood, the cosmic web, that vast interconnected structure stretching across hundreds of millions of light years, is a local feature. Laniakea, the supercluster containing the Milky Way, is a local feature. The entire observable universe, with its 2 trillion galaxies and trillion stars, is a local feature, a patch, a bubble, a single data point in a dataset so large that we'll never see the rest. And if the universe is infinite, then the cosmic web doesn't end, it repeats. Variations on the same theme, filaments and voids and clusters, stretching outward forever, filling infinite space with infinite structure. The pattern we see in our bubble is not unique, it's universal. Every observable universe looks roughly the same because the laws of physics are the same everywhere, and the initial conditions set by inflation were smoothed out across all scales. The cosmic web is everywhere. Laniakea is everywhere. The Milky Way, or something very much like it, is everywhere. And Earth, or something very much like it, is everywhere, infinitely many times. In an infinite universe, uniqueness is impossible. Everything that can exist does exist, and everything that does exist is repeated infinitely many times in infinitely many configurations across an infinite expanse. The philosophical implications are staggering. If the universe is infinite, then nothing you do matters on a cosmic scale because someone else, somewhere infinitely far away, is doing the exact same thing. And someone else is doing the opposite, and someone else is doing something entirely different. Every choice, every action, every moment of your life is replicated infinitely many times in regions beyond the horizon. You are not unique. Earth is not unique. Humanity is not unique. We're just one instance of a pattern that repeats forever. That idea should feel diminishing. It should make everything seem meaningless. But it doesn't have to. Because even if there are infinite copies of you scattered across an infinite universe, you're still here, this version of you, in this place, at this moment, and this is the only version you'll ever experience. The others, if they exist, are beyond your reach, beyond your observation, beyond your ability to interact with or influence. they might as well not exist. For all practical purposes, the observable universe is all there is, not because nothing exists beyond it, but because nothing beyond it can ever affect you. The horizon is a one-way mirror. We can't see out, and nothing beyond it can see in. The bubble we live in is the only bubble that matters. The universe beyond the observable is not empty speculation. It's a logical consequence of the properties we've measured. Flatness, inflation, the uniformity of the cosmic microwave background, all of those observations point to a universe that extends far beyond what we can see. The question is not whether there's more. The question is how much more, and whether we'll ever find a way to constrain it. Right now, the answer is no. We can't measure it. We can't observe it. We can only infer it from models that extrapolate far beyond the data. And those models, as good as they are still just models. They could be wrong. The universe could be smaller than we think. It could be shaped differently. It could stop obeying the laws we've measured in our local bubble once you get far enough out. We don't know. We can't know. The only way to find out would be to travel beyond the horizon, and that's impossible. The expansion of space is faster than light at those distances. You could never catch up. Even if you could somehow travel at the speed of light, which you can't, you'd never reach the edge of the observable universe because the edge is receding faster than you're moving. The horizon is a boundary you can approach, but never cross. Some cosmologists have suggested that the universe might not be infinite even if it's flat. They've proposed that space could be finite but unbounded, shaped like a torus or some other closed topology that has no edge but also no infinite extent. In a toroidal universe, if you traveled far enough in one direction, you'd loop around and come back to where you started, like a character walking off the edge of a video game screen and reappearing on the other side. That kind of universe would be finite, with a measurable size, but it would still be much larger than the observable universe. The constraints from the cosmic microwave background rule out small toroidal universes. If space is shaped like a torus, the loop has to be so large that we can't detect it, which means the universe would still be enormous, hundreds or thousands of times larger than the observable region, even if it's not infinite. Either way, the observable universe is a tiny fraction of the whole. The observable universe is shrinking, not in size. The radius is still 46.5 billion light-years, but in content. Galaxies at the edge are disappearing, redshifted into invisibility as the accelerating expansion carries them beyond the cosmic event horizon. Every year, more galaxies cross that boundary and are lost forever. In a few tens of billions of years, the only galaxies we'll be able to see are the ones in our immediate neighborhood, the local group. Maybe the Virgo cluster. Everything else will have been carried away by the expansion. The observable universe will still exist. It will still have a horizon, but it will be almost empty. A handful of nearby galaxies drifting in a vast dark expanse, surrounded by the faint glow of the cosmic microwave background. Future civilizations, if any exist, will look up at the sky and see almost nothing. No distant galaxies, no cosmic web, no evidence that the universe extends beyond their local region. They'll think they're alone in an empty cosmos, and they'll have no way to prove otherwise. The evidence will have been erased by the expansion. The universe is hiding its own history, and we're living in one of the last eras when that history is still visible. That makes the observable universe a time-limited resource, a window of opportunity. We can see the distant galaxies now because the light from them has had time to reach us. But that window is closing. The farthest galaxies are already disappearing. The ones Webb is observing at redshift 1415, sitting near the edge of the observable universe, are on the verge of being lost. In a few billion years, the light from those galaxies will have been stretched so far by the expansion that it will be undetectable. The galaxies themselves will still exist, probably, though they'll have merged and evolved into something unrecognizable. But we'll never see them again. The horizon is shrinking, and the universe beyond the horizon is growing larger. The total universe, whatever its size, is expanding. The observable universe is getting smaller in content, and the gap between what exists and what we can see is widening every second. The true scale of the universe is unknowable. That's the bottom line. We can measure the observable universe. We can map it, catalog it, study its structure and evolution. But the total universe, the full extent of space and matter and energy, is beyond our reach. It might be infinite, it might be finite, but so large that the difference doesn't matter. Either way, the observable universe is a bubble, a tiny fraction of a whole we'll never see. And that's not a failure, that's just the way things are. The universe doesn't owe us visibility, it doesn't owe us answers. It's under no obligation to be comprehensible or measurable or small enough to fit inside a human imagination. It just is, vast beyond measure, possibly infinite. And we're sitting in a small corner of it, looking out at a horizon we can't cross, trying to piece together a picture of something too large to ever fully see. The scale defeats intuition. It defeats analogy. It defeats language. And still, we keep trying to describe it, because that's what humans do. We measure, we map, we name, we build models, and we test them, and we refine them, and we push the boundaries of what we can know a little bit farther every year. The true scale of the universe is incomprehensible, but the attempt to comprehend it, the effort to understand even a fraction of what's out there, is worth making. Because the alternative is to stop looking, and we're not built to stop. The observable universe is not the universe. The cosmic web stretches beyond what we can see. The horizon sits 46.5 billion light-years away, and past that edge, space keeps going. Galaxies, stars, filaments, voids, all of it continues into regions we will never observe because the light hasn't had time to reach us and never will. The universe might be infinite. It might be so large that infinity and merely incomprehensible are functionally identical. Either way, everything we've talked about, every structure, every galaxy, every measurement, all of it is local, a map of our neighborhood. A single patch in something vastly unimaginably larger. And that should feel like the end of the story, the final revelation, the last rung on the ladder, except it's not. Because there's one more step, one more layer to peel back, and it's the most uncomfortable one. It's not about distance, it's not about time, it's about us, about the thing doing the observing, the human brain. The 3-pound lump of neurons sitting inside your skull, trying desperately to make sense of numbers that were never meant to fit inside it. This is where the scale stops being about the universe and starts being about the gap between what exists and what we can process. The disconnect between cosmic reality and human perception. And that gap is not small, it's a chasm. An abyss so wide that every analogy we've used, every metaphor, every attempt to make the numbers relatable has been a lie by necessity. Because the truth is, your brain cannot hold this. It was never built to. Start with what the brain was built for. Humans evolved on the African savanna roughly 300,000 years ago. Our ancestors were hunter-gatherers, moving in small groups, tracking animals, gathering plants, avoiding predators, navigating terrain that stretched maybe a few dozen kilometers in any direction. The challenges they faced were immediate. Is that rustling in the grass a threat? How far is it to the next water source? Can I reach that tree before the lion reaches me? The brain evolved to answer those questions. It developed an intuitive sense of distance, but only for distances that mattered to survival. You can look at a tree 50 meters away and estimate how long it would take to run there. You can glance at a hill on the horizon and judge whether it's worth the walk. You can throw a rock at a target and your brain calculates the trajectory without conscious thought, adjusting for distance, gravity, wind. That's what the brain is good at. Immediate, human-scale problems. Distance is measured in steps, time measured in heartbeats, quantities measured in handfuls. Push beyond that range and intuition breaks. You can't intuitively grasp the distance to the next city. You need a map, you need numbers, you need tools that translate abstract measurements into something your brain can work with. The distance from New York to Los Angeles is roughly 4,000 kilometers. You don't feel that distance. You don't experience it as a unified thing. You experience it in pieces, hours on a plane, days in a car, segments that your brain can chunk into manageable units. The brain cheats. It breaks large things into small things and processes the small things one at a time. That works for human-scale distances. It stops working somewhere around the distance to the moon. Beyond that, the numbers are just numbers, abstractions. You can memorize them, you can write them down, you can do math with them, but you can't feel them. You can't hold them in your mind the way you can hold the image of a tree or a hill or a city skyline. The same is true for quantities. Humans are good at estimating small numbers. Show someone a handful of objects, anything up to about 5 or 6, and they can tell you how many there are without counting. The brain recognizes the pattern instantly. Push it higher, 10, 15, 20, and people start guessing. They chunk, they group. 3 clusters of 4 is 12. 2 rows of 7 is 14. The brain needs structure to handle quantities larger than a handful, and past a certain point, it stops trying. 1,000 is not a number you can visualize, neither is 1,000,000 or 1,000,000,000. Those words stop meaning anything concrete. They become placeholders for the idea of bigness. 1,000,000 sounds big. 1,000,000,000 sounds bigger, but the difference between 1,000,000 and 1,000,000,000 is not intuitive. 1,000,000 seconds is about 11.5 days. 1,000,000,000 seconds is almost 32 years. The gap between those two numbers is enormous, but the brain doesn't register it that way. Both are just big. And a trillion, a quadrillion, those aren't even pretending to be intuitive. They're math, abstract. Symbols on a page that the brain processes the way it processes any other piece of information, by filing it away under the label very large and moving on. Time is worse. The human brain experiences time as a sequence of moments stitched together into a narrative. You remember the past. You anticipate the future. You experience the present as a thin sliver, a moving window that slides forward at 1 second per second. The brain can hold maybe a few seconds of sensory memory in active awareness. After that, it's gone, filed into long-term storage or discarded. You can remember events from years ago, but you don't experience them the way you experienced them at the time. Memory is reconstruction. A story the brain tells itself about what happened, edited and compressed and reinterpreted every time you access it. The brain doesn't experience years or decades as continuous stretches. It experiences highlights, moments, the day you graduated, the summer you spent at the beach, the year your parent died. Everything else fades into a vague background, a sense that time passed but without the detail. And anything beyond a human lifetime stops being experiential at all. 100 years is history. 1,000 years is ancient history. 1,000,000 years is geology. 1 billion years is cosmology. None of those timescales exist in the brain's native framework. They're abstractions, understood only through analogy and comparison, never through direct experience. Here's the problem. The universe operates on scales that are not just larger than human intuition. They're larger by factors that themselves are incomprehensible. The observable universe is 93 billion light-years across. A light-year is about 9.5 trillion kilometers. Multiply those two numbers and you get the diameter in kilometers. Then multiply by pi and divide by 2 to get the circumference. Then calculate the volume. Every one of those steps involves numbers so large that the human brain has no framework for them. You can write them down, you can plug them into a calculator, you can get an answer, but the answer doesn't mean anything. Not in the way that 50 meters or 4,000 kilometers means something. Those are distances you can relate to your body, to your experience. 93 billion light-years is not. It's a number, a label, a way of saying this is the size of the thing, but the thing itself is beyond comprehension. The same is true for mass. The sun weighs about 2 times 10 to the power of 30 kilograms. That's a 2 followed by 30 zeros. The Milky Way weighs about 1.5 times 10 to the power of 42 kilograms. The observable universe contains about 10 to the power of 53 kilograms of ordinary matter. Those numbers are not small. They're not even medium. They're so large that the human brain treats them as functionally equivalent. Big, very big, incomprehensibly big. The differences between them, differences that span factors of a trillion or a trillion, don't register. The brain has no intuition for scale at that level. It's all just big, and yet we keep trying. We build analogies, we scale things down. If the sun were the size of a basketball, Earth would be a peppercorn sitting 30 meters away. If the Milky Way were the size of North America, the solar system would be a coin. If the observable universe were the size of Earth, the Milky Way would be the size of a single cell. Those comparisons help. They give the brain something to latch onto, a way of translating the incomprehensible into something almost comprehensible. But they're still lies, because even the scaled-down versions are too large to hold. You can imagine a basketball, you can imagine a peppercorn, but you can't imagine 30 meters of empty space between them and hold that image in your mind while simultaneously remembering that the peppercorn is an entire planet with oceans and continents and billions of people. The brain can't do it. It toggles. It switches between the macro view and the micro view, but it can't hold both at once. The scale defeats it. Carl Sagan understood this. In 1990, he convinced NASA to turn the Voyager 1 spacecraft around and take a photograph of Earth from the edge of the solar system. The image is famous now, a pale blue dot, Earth, reduced to a single pixel, suspended in a beam of scattered sunlight. Voyager was about 6 billion kilometers away when it took that picture. 6 billion. And from that distance, Earth was invisible. Not small, invisible. The only reason the dot shows up in the image is because sunlight happened to reflect off the planet at just the right angle to hit the camera. Sagan wrote about that image in a way that cuts through every abstraction and analogy and metaphor we've used so far. He said, "Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on that dot. Every saint and sinner, every young couple in love, every mother and father, every inventor and explorer, every corrupt politician, every hero and coward, every civilization that ever rose and fell, all of it happened there, on a mote of dust, suspended in a sunbeam. That's the scale. That's the reality. Everything we've ever built, every war we've ever fought, every idea we've ever had, All of it happened on a rock so small that from the edge of our own solar system, it's a pixel, and the solar system is nothing, a speck in the Milky Way, and the Milky Way is nothing. A single galaxy in a supercluster, and the supercluster is nothing, a thread in the cosmic web, and the cosmic web is nothing. A local structure in an observable universe that itself is nothing compared to the universe beyond the horizon. The math is clear, the observations are solid, the scale is real, and the human brain, sitting in your skull right now, processing these words, cannot hold it. You've read this far. You've followed the numbers. You understand, intellectually, that the universe is enormous, that the distances are vast, that the structures are incomprehensibly large. But you don't feel it. You can't. Because feeling requires intuition, and intuition requires experience, and you have no experience with distances measured in billions of light years, or masses measured in trillions of solar masses, or timescales measured in billions of years. The universe is not built for you. It was not designed with human comprehension in mind. It doesn't care that your brain can't hold it. It doesn't care that the numbers are too large, or the distances are too vast, or the timescales are too long. It just is. And you, standing on your mote of dust, staring up at the sky, trying to make sense of it, are doing the best you can with a brain that evolved to throw rocks at rabbits. Here's the humbling part. Everything we've talked about, every chapter, every scale, every structure, all of it is provisional. A best guess based on the data we have right now. The age of the universe is 13.8 billion years, give or take. The size of the observable universe is 93 billion light-years across, give or take. The number of galaxies is 2 trillion, give or take. Every one of those numbers has error bars, margins of uncertainty, ranges where the true value might sit, and those ranges are huge. The distance to the edge of the observable universe could be off by a few billion light-years, and it wouldn't change the fundamental picture. The total number of galaxies could be off by a factor of 2 or 3, and we'd shrug and update the models. The mass of the Milky Way was revised downward by a factor of 10 in 2023, and most people didn't even notice. The universe is too large for precision to matter at the scales we've been discussing. We're drawing maps with crayons, the details are fuzzy, the edges are blurred. And we're standing so close to the thing we're trying to map that we can't see the whole picture. We're inside the structure, inside the observable universe, inside the cosmic web, inside the Milky Way. We're trying to measure the size of a forest while standing in the middle of it at night with a flashlight, and every tree we can see tells us something about the forest, but we'll never see the whole thing. The best we can do is extrapolate, guess, build models and test them and refine them and accept that every answer we get is incomplete. And still, we try, because that's what humans do. The brain might not be built to comprehend the universe, but it's built to try. It's built to ask questions, to measure, to explore, to push the boundaries of what's known a little bit farther every year. The first humans who looked up at the night sky and wondered what the stars were didn't have telescopes. They didn't have math. They didn't have the tools to answer their questions, but they asked anyway. And their descendants built the tools, invented the math, launched the telescopes, mapped the cosmic web, measured the age of the universe, found galaxies at the edge of the observable horizon, and we're still going. The James Webb Space Telescope is finding galaxies that shouldn't exist. Euclid is mapping the large-scale structure. Future missions will push farther, see deeper, collect more data. The boundaries of what we know are expanding. Slowly, incrementally, but they're expanding. And every new discovery makes the universe feel a little bit larger, a little bit stranger, a little bit more incomprehensible than it did before. That should be discouraging. It's not, because the incomprehensibility is the point. The universe is not obligated to make sense. It's not required to fit inside a human imagination. It's not designed to be comfortable or intuitive or easy to grasp. It just is. And the fact that we can measure it at all, that we can map it and catalogue it and build models that predict its behavior with extraordinary precision is astonishing. The fact that a species of apes standing on a rock orbiting an unremarkable star in an unremarkable galaxy can look out at the cosmos and figure out that it's 13.8 billion years old and 93 billion light-years across and made mostly of dark matter and dark energy is one of the most improbable achievements in the history of the universe. We shouldn't be able to do this. Our brains aren't built for it, and yet here we are, writing equations, building telescopes, staring at the edge of everything and refusing to look away. The universe's indifference is not a flaw, it's a feature. The cosmos doesn't care about you. It doesn't care about Earth. It doesn't care about humanity or our wars or our art or our dreams. It doesn't care that we exist. It would keep running exactly the same way if we disappeared tomorrow. Stars would keep burning. Galaxies would keep colliding. The expansion would keep accelerating. The cosmic web would keep dissolving at the edges, galaxies disappearing beyond the horizon, the observable universe slowly emptying out until nothing remains but a handful of nearby objects drifting in the dark. That process doesn't need us. It doesn't notice us. We're not part of the equation. We're just observers, temporary, fragile, standing on a rock that will one day be swallowed by its own sun, staring out at a universe that will keep going long after we're gone. And that's fine. That's how it should be. Because the universe doesn't exist to validate our importance. It exists, that's all. And the fact that we're here to see it, to measure it, to try to understand it, is enough. The journey from Earth to the edge of the observable universe is a journey through scale. From a planet 12,000 kilometers wide to a solar system measured in light hours, to a galaxy 100,000 light-years across, to a supercluster 500 million light-years wide, to a cosmic web stretching across billions of light-years, to an observable universe 93 billion light-years across, to a total universe that might be infinite. Every step is a leap. Every new structure is orders of magnitude larger than the one before it, and at every step the brain struggles to keep up. It invents new units, new analogies, new ways of cheating, of breaking the incomprehensible into pieces small enough to process. And every time, the pieces are still too large. The scale still defeats intuition. The numbers still refuse to fit. And that's the point. The scale of the universe is not a puzzle to be solved. It's not a problem with a solution. It's a fact, a reality. The universe is enormous, and you are small, not metaphorically, literally. You're small. Your planet is small. Your solar system is small. Your galaxy is small. Your supercluster is small. The entire observable universe, with its 2 trillion galaxies and trillion stars, is small compared to what lies beyond the horizon. The scale doesn't care about your feelings. It doesn't care that the numbers are too large, or the distances are too vast, or the timescales are too long. It just is. And you, standing here, reading this, processing these words with a brain that was never designed for this task, are doing the best you can. The humility that comes from understanding scale is not the humility of defeat, it's the humility of perspective, of recognizing that you are not the center of the universe, that your problems, as real as they are to you, are not cosmic problems, that the things you worry about, the things that feel urgent and important and all-consuming, are local, temporary, bound to a single moment on a single planet, in a single galaxy, in a universe so large that your entire existence is a rounding error. That realization doesn't make your life meaningless, it makes it precious, because you're here, right now, in this moment, on this rock, under this sky. And you have the ability, the privilege, the absurd good fortune to look up at that sky and ask questions about what's out there, to wonder, to explore, to measure the universe and find out that it's larger than you ever imagined, and then to realize it's even larger than that, and then to realize it's even larger than that, and to keep going anyway. The universe will outlast you. It will outlast your children, your civilization, your species. It will outlast the sun, the Milky Way, the local group. It will keep expanding long after every star has burned out, and every black hole has evaporated, and every structure has dissolved into a thin, cold soup of particles drifting through an infinite void. The universe doesn't care. It never did, and that's okay. Because you're not here to matter on a cosmic scale. You're here to matter on a human scale, to the people around you, to the moment you're living in, to the small patch of space and time you occupy. And that's enough. It has to be, because it's all you get. The incomprehensibility is not a bug. It's the entire point. The universe is too large to fit inside your head. It always has been. It always will be. And the moment you accept that, the moment you stop trying to force the numbers into intuition and just let them be what they are, is the moment you start to understand what you're looking at. Not in the way you understand a tree or a hill or a city, but in the way you understand an idea, a concept, a fact that exists independent of your ability to experience it. The universe is 93 billion light-years wide, probably larger, possibly infinite, and you, standing on your rock, staring up at the sky, are the only thing in your observable universe that knows it, that matters, not because it changes the universe, but because it changes you. You started this journey standing on a planet, a rock 12,000 kilometers wide, spinning through space at speeds you'll never feel. You knew it was big, you thought you understood scale, and then we left. We crossed the solar system, a gap so vast that light takes hours to traverse it, and you realized the space between things is larger than the things themselves. We moved to the stars, and the distances stopped making sense. 4 light-years to the nearest neighbor, 100,000 light-years across the Milky Way, numbers that your brain filed away under very large and moved on. Then we climbed higher, the local group, Laniakea, the cosmic web. Structures so immense that galaxies, entire galaxies containing hundreds of billions of stars, became pixels in a map you'll never see the edges of. And still we kept going. To the observable horizon, 93 billion light-years away, where the light from the earliest galaxies is still arriving after 13 billion years of travel. And beyond that, into the space we can't observe, the universe that extends past every telescope, past every measurement, possibly forever. And now you're here, at the end, except it's not the end, because the universe didn't stop when you finished reading. It's still out there, still expanding, still dissolving at the edges as galaxies disappear beyond the horizon, swallowed by the acceleration of space itself. The cosmic web is still threading through the void. Laniakea is still pulling everything toward the great attractor. The Milky Way is still orbiting its center, carrying you with it at hundreds of kilometers per second through a galaxy you'll never escape. And Earth is still spinning beneath your feet, oblivious, ordinary, the only home you'll ever know. The scale hasn't changed. The universe is exactly as large as it was when you started. What changed is you. You looked, You climbed the ladder. You followed the thread from your doorstep to the edge of everything and found out that the edge isn't an edge at all. It's a horizon, a boundary of visibility, not existence. The universe continues. It always has. And it will keep going long after the last human closes their eyes for the last time, and the Earth is a cinder, and the Sun is a cold white dwarf drifting through a galaxy that no longer remembers it was ever alive. That should feel crushing. It doesn't, because here's the thing, you're still here. Right now, on this rock, under this sky, staring up at a universe that has no obligation to be comprehensible and never will be. And you figured it out anyway. Not all of it, not even most of it, but enough.